Picture this. You're floating in the bone-chilling silence of space, more than 3 times farther from the sun than Earth ever gets. Out here, sunlight is barely a whisper. Ice stays frozen solid. Comets go dormant. Everything sleeps. And then you see it, a comet absolutely hemorrhaging water into the void, dumping 40 kilograms of the stuff into space every single second. Not a trickle, but a full-blown flood. Water gushing off a frozen rock where water has no business flowing at all. This is 3 Atlas, an interstellar comet that crashed into our solar system from somewhere else entirely, bringing rules from another star's backyard. And those rules, they don't match ours. Not even close. The first red flag came from Swift, a space telescope designed to hunt gamma bursts. Swift aimed its ultraviolet eyes toward 3 Atlas in early 2025 and spotted something that shouldn't exist, a halo of hydroxyl molecules surrounding the comet. Hydroxyl O is what you get when sunlight rips water molecules apart. It's the echo of water screaming as it dies. When you see O, you know water was just there, and Swift saw a lot of it. The numbers are at a distance of 3.51 astronomical units from the Sun, that's more than 3 times Earth's distance. 3 Atlas was releasing 1.35 times YY water molecules every second. That's 40 kilograms per second, every single second. To put that in perspective, that's like dumping a small car's worth of water into space every minute at a distance where our comets barely whisper. Our solar system comets don't do this. Not out here. This far from the sun, they're cold, dormant, practically dead. Water ice needs heat to sublimate, to turn directly from solid to gas, without melting in between. And there's just not enough solar energy this far out to drive that kind of activity. Our comets wait until they're much closer to the sun before they wake up and start streaming gas and dust into space. 3 Atlas clearly didn't get that memo. You might remember Alma, the first confirmed interstellar visitor. That thing was dry as a bone. No water, no outgassing, just a tumbling rock speeding through our neighborhood. Silent, then came to Borisov, the second interstellar comet. Boris was active, sure, but it behaved exactly like our comets do. It followed the script. It was predictable. It was boring in the best possible way. 3 Atlas is neither of those things. It's alive in a way that shouldn't be possible. It's screaming water into space where silence should reign. And the question hanging over every astronomer who's pointed a telescope at this thing is simple. How? What mechanism could possibly drive this? Is there some exotic ice we don't know about? Something that sublimates at temperatures we thought were too cold? Is the comet's interior still warm from its birth billions of years ago? Is it rotating in some weird way that focuses sunlight onto hidden reservoirs of volatile materials? Or is there chemistry happening inside that rock that we've simply never encountered before? The water is just the beginning. 3 Atlas is also leaking other things. Cyanide, nickel, carbon dioxide in concentrations that make no sense. Each new observation adds another layer to the mystery. Each spectral line that shows up in the data is another question mark. This isn't just a comet behaving oddly. This is a comet that seems to be operating under a completely different set of physical rules. Rules written in another star system under different conditions with different chemistry. And now it's here in our solar system, giving us a front row seat to processes we've never seen before. The thing that keeps astronomers up at night is this: if free Atlas is doing things our comets can't do, what does that tell us about where it came from? What kind of star system builds comets like this? What were the conditions in that protoplanetary disk billions of years ago? And most provocatively, this comet just weird? Or is it a messenger carrying news about how different the universe can be? Every telescope that can see this thing is now pointed at it. Spectroscopy, photometry, polarimetry, every tool we have, because 3E Atlas isn't just a curiosity. It's a window, a crack in our understanding. And through that crack, we might glimpse something extraordinary. All right, so we've got this interstellar comet dumping water into space like it's going out of style, completely breaking the rules we thought were set in stone. But if you thought that was weird, buckle up, because the plot thickens. The water was just the appetizer. The main course is a discovery so baffling it's making astronomers question everything they thought they knew about cosmic chemistry. Here's the deal with comets in our neighborhood. They follow a pretty reliable playbook. When they get close enough to the sun and things start heating up, metals begin to sublimate. That is, they turn directly from a solid into a gas. And when this happens, iron and nickel show up together like two old friends who always travel in pairs. You see one, you see the other. It's one of those cosmic constants, a fundamental rule of the solar system game. They're locked together in the same mineral structures, formed in the same stellar furnaces, and they sublimate at roughly the same temperatures. They're a package deal, the whole 9 yards. Well, 3E Atlas clearly never got the memo on that one either. The Very Large Telescope in Chile, a beast of an instrument with a mirror the size of a swimming pool, aimed its spectrograph at this cosmic renegade. A spectrograph is like a super-powered prism that splits light into a rainbow, revealing the chemical fingerprints of whatever it's looking at. And what it found made scientists' jaws drop. Blazing bright in the spectrum were the emission lines of nickel, strong, unmistakable, impossible to ignore, but iron, either completely absent or so faint it barely registered on the detectors. It was like finding smoke without a fire, like finding footprints without any feet to make them. In our solar system, this just doesn't happen, period. Let's get specific. At around 2.8 astronomical units from the Sun, astronomers measured nickel pouring off the comet at a rate of about 5 grams per second. Now, 5 grams might not sound like much. It's about the weight of a sheet of paper. But when you realize that's happening continuously, second after second, with iron nowhere in sight, it's not a glitch. It's a pattern. It's the comet screaming a fundamental truth about its own makeup. And that truth is completely alien to us. So, what in the universe could possibly explain this? The scientific community has been tossing around theories, and none of them are simple. Let's walk through the leading suspects. First up, chemical fractionation. This is the idea that in the cosmic nursery where 3E Atlas was born, the conditions were just right for nickel and iron to go their separate ways. Maybe nickel got incorporated into volatile compound substances that evaporate easily, while iron got stuck in more stubborn, refractory minerals that need way higher temperatures to sublimate. Picture it like this. Nickel hitched a ride on the back of volatile ices while iron got left behind, trapped in rocky grains that wouldn't budge unless things got really, really hot. This could create the exact decoupling we're seeing billions of years later. Next theory on the table involves something called organometallic compounds. On Earth, we have molecules like nickel carbonyl, where nickel atoms bind to carbon monoxide. These things are notoriously volatile. They evaporate at relatively low temperatures. Now, imagine 3E Atlas formed in an environment rich in carbon monoxide and other organic molecules. It's possible that nickel got trapped in these kinds of compounds, essentially hiding in plain sight. Then, when sunlight hits the comet, these molecules break down, releasing pure atomic nickel into the coma, the fuzzy cloud of gas surrounding the nucleus, while the iron remains locked away tight in solid grains. It's a neat explanation, but it requires a very specific chemical recipe to be present during the comet's formation. Then there's the slow, grinding process of space weathering. For millions, maybe billions of years, this comet has been a cosmic target, bombarded by high-energy cosmic rays and brutal ultraviolet radiation from stars it's passed. That kind of sustained assault can do weird things to surface chemistry. It's possible that this radiation processing created nickel-rich surface layers while the iron got buried deeper, or was chemically altered into something we can't easily detect. In this scenario, the nickel we're seeing isn't representative of the comet's core composition. It's just the skin, a radiation-damaged rind that doesn't tell the whole story. But here's the most mind-bending possibility of all. What if 3E Atlas formed in a stellar system with a genuinely different chemical recipe? Stars aren't all stamped from the same cookie cutter. Older stars, stars from different parts of the galaxy, stars that formed from gas clouds enriched by different types of supernovae, they all have slightly different compositions. Maybe 3E Atlas comes from a place where nickel was just way more abundant relative to iron than it is in our corner of the cosmos. Maybe its birth star was chemically odd, and that oddness is now written into every single molecule of this comet, a permanent record of its alien heritage. Of course, we have to pump the brakes a little here. Spectroscopy is incredibly difficult. Detecting faint emission lines against the bright background of space is like trying to hear a whisper in a hurricane. There are thresholds of detectability. It's entirely possible that iron is there, just lurking below our current detection limits. Maybe the iron emission is blended with other spectral features hiding in plain sight. Maybe we're just looking at the wrong wavelengths. As the comet gets closer to the sun and heats up even more, iron might start to appear. That would be reassuring in a way. It would mean the universe still plays by rules we can understand. But what if it doesn't? What if 3E Atlas gets all the way to perihelion? That closest shave with the sun and iron never shows up. What if the nickel-to-iron ratio stays completely inverted compared to everything we've ever seen? That wouldn't just be surprising, it would be revolutionary. It would tell us, in no uncertain terms, that planetary systems can produce comets with metal chemistry so fundamentally different from ours that our models need a complete overhaul. From the ground up, this is why astronomers are watching 3E Atlas so obsessively. Every observation is a test. Every spectrum is a chance to either confirm our understanding of the cosmos or shatter it into a million pieces. And right now, 3E Atlas is doing a whole lot more shattering than confirming. So, we've established that 3E Atlas is dumping water where it shouldn't, and shedding nickel without its trusty sidekick, iron. It's already broken the first 2 rules of the Solar System Club. But you know what? It's not done. Not by a long shot. This comet is just getting warmed up, and its next trick is something that feels less like a natural process and more like a deliberate, calculated performance. Let's talk about how comets are supposed to behave. The physics, on paper at least, is beautifully simple. As a comet approaches the sun, it should brighten in a smooth, predictable, almost boring way. More sunlight means more heat, which means more ice sublimating, which means more gas and dust being released. It's a gradual ramp-up, like slowly turning up a dimmer switch. The relationship between distance and brightness should follow a neat mathematical curve. It's reliable. It's dependable. 3E Atlas, once again, looked at that rulebook and decided to use it for kindling. Observers keeping a close eye on this cosmic visitor noticed something bizarre happening with its color. Early on, when it was still out in the cold, dark depths, the comet looked relatively neutral, maybe with a slightly reddish tint, which is pretty typical for distant, icy bodies. But as it began its inward plunge, getting closer and closer to the sun's warmth, it started to change. It didn't just get brighter. It started turning an unmistakable, vivid, almost eerie green. This wasn't a subtle shift you had to squint to see. This was a full-blown color change that dominated every photograph. So, what's the deal with the green? It's coming from 2 sources, both of which we've already touched on. Cyanide molecules and, you guessed it, that strange, standalone atomic nickel. Both of these substances emit light incredibly strongly in the green part of the spectrum. And as the comet warmed up, their emissions didn't just increase. They exploded, ramping up so dramatically that they painted the entire coma in this otherworldly glow. But here's where it gets really wild. The increase in brightness wasn't linear. It wasn't even following that smooth, predictable curve we expect. It was That's a fancy way of saying the emission lines were intensifying way faster than simple geometry would predict. Think about it this way. When you have the distance to the sun, you get 4 times the sunlight per square meter. That's the inverse square law. Basic Astrophysics 101. But 3E Atlas's emissions were climbing even faster than that. It was like the comet was not just getting more sunlight, but was somehow amplifying it. Unlocking something new from within. Astronomers have a name for this kind of behavior. Switch on. Imagine a temperature threshold, a specific point on a thermostat. Below that threshold, a particular type of ice stays solid, locked away, dormant. The comet crosses that invisible line in space, and suddenly click, that ice starts sublimating like crazy. The gas production jumps. New emission lines appear in the spectrum. It's not a gradual process. It's like flipping a light switch. One moment the process is off, the next moment it's on, full blast. And once it's on, it can run away with itself if there's enough material to feed it, creating a runaway chain reaction of sublimation. It seems 3E Atlas doesn't just have one switch. It has a whole control panel of them. The water turned on first. way out at 3.5 astronomical units, which was already weird enough. Then, as it got closer, the cyanide and nickel switches flipped, blazing green as the comet hit a new temperature sweet spot. Each new emission suggests a different volatile reservoir is being tapped, a different chemical pocket reaching its activation temperature. It's like the comet is a complex machine with multiple systems, and each one is coming online in sequence as it warms up. So, what could possibly explain this bizarre multi-stage activation? Scientists have a few compelling theories, each one painting a fascinating picture of the comet's inner life. One model involves something called extended icy grains in the coma. Instead of all the action happening right on the surface of the nucleus, imagine small ice grains being constantly chipped off and lifted away by the gas that's already escaping. These tiny grains drift away from the comet, still cold, still frozen solid. But as they float through space, they're exposed to more and more direct sunlight. Eventually, each individual grain reaches its own personal sublimation threshold and starts to turn to gas. This creates a distributed source of activity, not just from the main body of the comet, but from a whole cloud of icy grains surrounding it, all popping like popcorn at different times. This could absolutely explain the superlinear brightness increase and the sudden appearance of new emission lines as different types of grains reach their boiling point. Another possibility is thermal fracturing. Comets are often called dirty snowballs, but that's an understatement. They're more like complex, porous structures of ice and rock all mixed together. When one part of the comet heats up and expands while another part stays cold and contracted, immense stresses build up inside. Eventually, something's got to give. The comet literally cracks. When an ice-filled crack opens up, it can expose fresh, pristine material that was previously insulated and protected from the sun. Suddenly, you have a massive new surface area sublimating, releasing a huge burst of new volatiles. The comet experiences an outburst. 3E Atlas might literally be cracking itself open as it heats, revealing layer after layer of frozen chemistry like a GEODE. Then there are the exotic ices. Water ice sublimates at one temperature. Carbon monoxide ice sublimates at a much lower temperature. Carbon dioxide is somewhere in between. If 3E Atlas is layered like an onion, with different ices trapped at different depths or in different regions, then as it warms on its journey inward, you'd see a sequence of activity. First, the supervolatiles, like carbon monoxide, would boil off. Then, the normal volatiles like water would kick in. Finally, the really stubborn stuff that needs a lot of heat would start to sublimate. Each layer peeling back is like turning the page to a new chapter in the comet's chemical story. Now, to be fair, this isn't entirely alien to us. We've seen comets in our own solar system do some pretty wild things. Some comets have sudden, violent outbursts, brightening by factors of 10 or more overnight. Some comets get torn apart by thermal stress as they approach the sun, their structural integrity simply giving up the ghost. Some comets stay completely dormant until they're almost on top of the sun and then suddenly explode into activity. But 3E Atlas is doing this on a schedule and at a distance that doesn't match anything in our experience. It's alive and kicking out where it should be fast asleep. It's switching on in ways that feel almost deliberate, almost programmed. And the tension is building. As 3E Atlas continues its death-defying dive toward the Sun, will more switches flip? Will we see new emission lines appear? New molecules we never even expected? Will the activity eventually plateau, or will it keep accelerating, getting more and more intense? Every week brings new data, and every week brings new surprises. This isn't a steady, predictable comet. This is a high-stakes drama unfolding in real time, and we all have front-row seats. Every cosmic nomad has a tale to tell, a story etched into its very path through the stars. Where it's going tells you where it's been, and when it comes to 3E Atlas, its trajectory is spinning a yarn that stretches across billions of years and thousands of light years. It's a story that makes this comet not just a visitor, but a ghost from a time long before our own sun was born. First, let's talk about its path. The orbit is what astronomers call hyperbolic. Forget the neat, looping ellipses that our planets follow. A hyperbolic orbit is a one-way ticket, an open curve that means this comet isn't from around here and it isn't staying. 3 Atlas came barreling in from the vast, empty spaces between the stars, took a sharp turn round our sun like a cosmic slingshot, and is now heading back out into the void, never to return. Its eccentricity is greater than 1, which in astrophysics speak means it's completely unbounded free agent, a wanderer just passing through our neighborhood. So, how do we know where it came from? This is where some serious cosmic detective work comes into play. Astronomers traced its path backward using something called precovery images. Think of it like digging through an old, forgotten photo album of the sky. Automated surveys have been photographing the heavens for years, often without anyone really looking at the individual images in detail. Researchers went back into these archives, knowing where to look thanks to the comet's calculated orbit, and found it. Turns out, 3E Atlas had been captured on film multiple times before anyone even knew it was interesting. Some of these images went all the way back to when the comet was a staggering 6.4 astronomical units from the Sun. Still a cold, distant speck on its long journey inward. By stitching together these old observations with the new data, astronomers managed to reconstruct its trajectory with incredible precision. And that trajectory, when traced backward, points outward, away from our solar system and deep into the Milky Way. But not just anywhere. This is where the story gets truly mind-bending. To figure out its point of origin, scientists combined this orbital modeling with data from the Gaia Space Telescope. Gaia is one of the most ambitious space missions ever launched. Galactic cartographer creating an incredibly precise 3D map of over 1 billion stars, charting their positions, distances, and movements. With this unprecedented map of the galaxy, astronomers could make an educated guess about the kind of stellar neighborhood 3 Atlas might have called home. The answer was nothing short of astonishing. Our galaxy has structure. The stars aren't just randomly scattered like salt on a table. Most stars, including our own sun, live in what's called the thin disk, a relatively flat, spiral-armed plane of younger, metal-rich stars orbiting the galactic center. It's the bustling, happening part of the Milky Way. But there's another component, a much more mysterious one, the thick disk. This is a population of older stars that orbit in more tilted, more eccentric paths. These thick disk stars are vertically puffed up, spread much farther above and below the main galactic plane. And crucially, they're chemically different. They're ancient, formed early in the galaxy's history when there were fewer heavy elements around. They have what astronomers call lower metallicity. 3 Atlas's trajectory strongly suggests it might have originated from this ancient thick disk. If that's true, if this comet really formed in that population of old-timer stars, then it could be significantly older than our own solar system. Our Sun and its planets are about 4.6 billion years old. Stars in the thick disk can be 7 billion years old, or even more. That means 3 Atlas could be carrying ice and rock from a time before the Sun even existed, a primordial relic from an earlier epoch of galactic history. Now, let that sink in for a second. Think about what that means chemically. The massive cloud of gas and dust that collapsed to form a thick disk. Star 7 billion years ago had a different recipe than the one that formed our Sun. Supernova explosions, the stellar furnaces that create and scatter heavy elements, have been enriching the galaxy over time. The earliest generations of stars had almost pure hydrogen and helium. Later generations, like our Sun, have a few percent of heavy elements mixed in. Stars in the thick disk are the middle generation. They have some heavy elements, but less than we do. If 3 Atlas formed in that ancient, less enriched environment, its very composition would reflect that lower metal. There would be less iron, less magnesium, less silicon ore, the rocky elements that are used to build planets. But there would still be plenty of the original volatiles, carbon, nitrogen, and oxygen locked into ethers and molecules. Maybe that's why we're seeing such a high carbon dioxide to water ratio. Maybe that's why the metal ratios look so bizarre. Maybe this comet isn't just from another star system. It's a chemical fossil from a time when the galaxy was younger and the periodic table was, in a sense, emptier. Of course, we have to be careful. Tracing an object back through billions of years of the gravitational chaos of the Milky Way is incredibly difficult. Gravitational tugs from passing stars, interactions with the spiral arms of the galaxy, all of that muddles the trail over eons. But the fact that it's even plausible that this comet in our sky right now could be older than our own world is nothing short of extraordinary. We might be looking at a survivor, a time capsule from the ancient galaxy, a tangible piece of a past we can only otherwise infer, and if we could someday pinpoint its birth cluster, the group of sibling stars that all formed together from the same gas cloud, we might even identify other members of its family that were also flung out into the galaxy. Other comets, maybe even rogue planets, now scattered across the cosmos. 3 Atlas might be just one letter in a message written across thousands of light years, and we're just now starting to learn how to read. Alright, so we've established that 3 Atlas is a cosmic rule breaker, an ancient traveler with a bizarre chemical makeup. But now we need to talk about what it's carrying. Because comets aren't just inert chunks of ice and rock hurtling through the void. Think of them less as asteroids and more as cosmic cargo ships, molecular libraries carrying the complete inventory of their birth environment. And 3 Atlas is hauling some of the strangest, most telling cargo we've ever seen. We've already talked about the water, that incredible 40 kilograms per second hemorrhaging into space at a distance where it should be frozen solid. That water, or more accurately, the hydroxyl fragments left behind when sunlight rips it apart, was the first clue that this comet was playing by a different rulebook. But honestly, the water is just the cover of the book. The real story, the part that's making planetary scientists do a double take, is what's inside. The real shock is carbon dioxide. Observations from multiple telescopes suggest that 3 Atlas has an extraordinarily, almost absurdly, high carbon dioxide to water ratio. In our solar system, comets are dominated by water. It's the main event, the primary volatile, the engine that drives their activity. Carbon dioxide is usually there, sure, but it's a supporting actor at best. 3 Atlas completely flips that script. Some measurements are suggesting that a staggering 95% of the volatile emissions streaming off this comet are carbon dioxide, with water being the minority component. Let that sink in. That's backward. That's inverted. That's like finding a forest where the trees are made of steel and the rocks are made of wood. It's nothing like what we see at home, and it fundamentally challenges our understanding of how comets are built. So, why would a comet be so carbon dioxide? Scientists have a few ideas, and they all point to a truly alien birthplace. One possibility is the temperature at which it formed. Carbon dioxide ice condenses from gas at a higher temperature than water ice. So, if 3 Atlas formed in a warmer region of its protoplanetary disk closer to its parent star than our comets typically form, it might have preferentially incorporated carbon dioxide ice while losing some of its more volatile water. Or maybe its parent star had a completely different radiation field, processing the ices in ways our Sun simply doesn't, or perhaps the giant planets in that system, if they existed at all, migrated differently, stirring up the disk and mixing materials in ways we wouldn't expect, creating bizarre hybrid compositions. Then there's the cyanide. Cyanide CN is actually pretty common in comets. It's the molecule that gives many of them their characteristic greenish glow. But in 3 Atlas, the cyanide showed up fashionably late, appearing after the water started sublimating later in the warming sequence. In our comets, cyanide and water tend to show up around the same time because they have similar sublimation temperatures. This delayed appearance in 3 Atlas suggests it might be sequestered differently. Maybe it's trapped inside complex organic molecules that need an extra jolt of energy to break down. Or maybe it's frozen in distinct layers beneath the water ice, waiting for its turn to be exposed. And of course, we can't forget the nickel. That atomic nickel glowing a brilliant green, completely separated from its usual partner, iron. We've already dove deep into that mystery, but it's worth emphasizing again. Every single element, every molecule we detect is a clue. Volatiles tell us about the temperature and pressure during formation. Refractory materials tell us about condensation sequences and thermal processing. The ratio of gas to dust tells us about the comet's structure and how icily it breaks apart. Now, let's talk about the elephant in the room. The idea that gets everyone's heart racing, the panspermia hypothesis. This is the notion that life, or at least the fundamental building blocks of life, can spread through space on comets and asteroids, seeding new worlds. 3 Atlas has water. It has organic. It has cyanide, which is a key precursor in prebiotic chemistry. If you were an alien chemist trying to design a comet to seed a planet with interesting, life-friendly chemistry, you'd include exactly these ingredients. But let's be crystal clear here. This is speculation. Full stop. There is zero evidence that 3 Atlas is carrying life. There is no evidence that any comet has ever carried living organisms. The panspermia hypothesis is intriguing, plausible in principle, but it remains completely unproven, and there are some serious deal-breaking problems with it. Cosmic radiation is brutal. Over millions or billions of years in interstellar space, high-energy particles tear apart complex molecules. Ultraviolet light from countless stars does the same. DNA, proteins, even simple amino acids can be shredded into their component atoms. For life to survive an interstellar journey, it would need to be buried deep, deep inside the comet, shielded by meters of ice and rock. But complex molecules might survive. Not living things, but chemical fossils. Molecules that were synthesized in the comet's parent system, perhaps in a planet's atmosphere or on its surface, and then got incorporated into the comet when it formed. Those molecules could potentially survive the long, cold journey if they're stable enough and well protected. And if we could analyze them, they might tell us things we can't learn any other way. They might reveal the atmospheric chemistry of an alien world. They might show us metabolic pathways from an extinct biosphere. They might be messages written in carbon and nitrogen and oxygen, waiting for someone with the right tools to decode them. This is why some scientists dream of intercepting one of these interstellar visitors. Not just observing it from a distance with telescopes, but sending a spacecraft to match its incredible velocity, to land on its surface, to drill into it, to scoop up samples and analyze them on the spot. The technological challenges are immense. Interstellar objects move incredibly fast, tens of kilometers per second relative to the Sun. Catching one would require a spacecraft already in position or capable of extraordinary acceleration. But the scientific payoff would be incalculable. A physical sample from another star system, chemistry from another corner of the galaxy. Answers to questions we've barely even learned to ask yet. 3 Atlas is already billions of kilometers away from the inner solar system, heading back out into the dark. We didn't catch it this time, but it's showing us what's possible. It's showing us what's out there, and it's making us hungry for more. Sometimes the most profound discoveries in science don't happen in a sterile lab or at the control panel of a billion-dollar telescope. Sometimes they happen because someone, somewhere, was looking at a puzzle in just the right way. Not with a complex algorithm or a machine learning model, but with the one tool we all have, the human brain. And sometimes that someone isn't a professional astronomer with a PhD and a tenure track. Sometimes it's just someone who loves the stars enough to look. Let me tell you about odd radio circles or ORCs. If you haven't heard of them, don't worry, you're not alone. They were only discovered in 2019, which in the grand, slow-moving world of astronomy makes them practically brand new. ORCs are exactly what they sound like. Vast, mysterious, circular structures visible only in radio wavelengths. You can't see them in optical light. You can't see them with infrared. Point a radio telescope at the right patch of sky, and boom, there they are. Perfect, enormous rings of radio emission, sometimes hundreds of thousands of light years across, just floating in space like cosmic smoke rings. The craziest part, nobody has a clue what they are. The leading theories involve galactic winds or shock waves from supermassive black holes. But honestly, that's just an educated guess. We're still largely in the dark. They are genuinely, deeply mysterious, and finding them is incredibly hard because they're faint and they tend to blend into the messy radio background of the universe. Automated detection algorithms, the workhorses of modern astronomy, tend to miss them completely. Why? Because they're trained to find things we expect to find, point sources like stars, compact objects like galaxies, things with defined shapes. They're not looking for giant, diffuse, perfectly round rings that look like something out of a sci-fi comic book. This is where a brilliant project called Radio at Home comes into the picture. This is a citizen science initiative, a global collaboration where volunteers from all walks of life can log on and visually inspect radio continuum maps. Their job isn't to look for anything specific. Their job is to look for weird, to be the first line of defense against the unknown, to flag anything that makes their brains say, "Huh, that's not right." And in March 2025, a volunteer did just that. They flagged something so extraordinary it sent ripples through the astronomical community. The object, with the catchy catalogue name ROJ 131346.9 plus 500320, is far more interesting than its name suggests. It's a pair of intersecting radio rings, twin circles overlapping in the sky to create a stunning, almost perfect figure-8 pattern. It's the most distant and most powerful orc discovered so far, and it was found not by a sophisticated AI, not by a professional survey team, but by a regular person volunteering their time to simply stare at data and look for things that don't belong. The discovery was made using low-frequency continuum maps from LOFAR. The low-frequency array, a sprawling network of radio telescopes spread across Europe. LOFAR chews through enormous amounts of data, generating a fire hose of information that's far too much for professional astronomers to examine by hand. Automated pipelines process most of it, flagging candidate objects based on brightness, shape, and other parameters. But those pipelines have filters. They have thresholds. They're designed to catch the expected, not the unexpected. This is where the raw, unfiltered power of human pattern recognition becomes invaluable. Our brains are incredible at spotting things that don't belong, at seeing structure in noise, at identifying something as interesting even when we can't immediately articulate why. The volunteer who found ROJ 131346.9 didn't need to know the complex physics behind ORC. They didn't need to understand the intricacies of radio interferometry. They just needed to look at the image and think, "That's weird." And they were absolutely right. But it's not just that one object. The Radio at Home project has flagged multiple anomalies that would have been lost in the data flood. Another volunteer found a giant radio galaxy with a peculiar ring structure around it that no model predicted. Another found a ring at the very end of a galactic jet, a feature that defied existing theories. These are objects that would have been archived and forgotten if human eyes hadn't been there to catch them. There's a massive lesson here that extends far beyond radio astronomy. We are entering an era of data deluge, a tsunami of information that threatens to overwhelm us. The Vera Rubin Observatory, currently under construction in Chile, is a prime example. When it comes online, it will generate a staggering 15 terabytes of data every single night. For context, that's like streaming high-definition video continuously for over 3 years. And it will do this every night for a decade. No human team can possibly look at all of that. No set of algorithms can catch every anomaly, every weirdness, everything that doesn't fit the existing templates. We need both. We need machines to handle the bulk processing, to sift through the noise and find the obvious signals. And we need humans to catch the weird edge cases, the outliers, the things that don't fit any existing model. It's a partnership between silicon and synapse. Now, let's connect this back to our main character, 3E Atlas. Could a citizen scientist have flagged its anomalies early? Could someone with access to public spectral data have noticed the nickel without tie-in signature before the professional teams published their findings? Could someone monitoring comet activity have looked at the early data and said, "Wait a second, why is this thing so active so far from the sun? That's not right." Maybe, maybe not. The data is complex, and professional training is essential for interpretation. But the point is, anomalies like 3E Atlas benefit from having as many eyes on them as possible. Professional astronomers have immense expertise, deep training, and critical context. But they also have expectations. They have models they're trying to confirm or disprove. They have limited time and immense pressure. Amateurs and citizen scientists come with fresh eyes, completely unburdened by what's supposed to happen. They're free to see what is actually happening. History is filled with stories of amateur astronomers making incredible discoveries. The Japanese amateur astronomer Kaoru Akiyama discovered multiple comets and a supernova. The British amateur Andrew Gray co-discovered an unusual stellar outburst. These aren't flukes. They are powerful examples of what happens when passionate people with telescopes or access to data decide to look carefully at the universe and ask their own questions in the future. As telescopes flood us with petabytes of data, citizen scientists might become the first responders to cosmic oddities. They might be the ones who flag the next interstellar comet, the next weird radio structure, the next thing that makes no sense. And when they do, professional astronomers will follow up, will investigate, will bring the full weight of scientific methodology to bear, and will figure out the physics. It's a partnership. And like all good partnerships, it's stronger, more resilient, and more creative than either component alone. Alright, so in our last chapter, we painted this beautiful, almost utopian picture of citizen science, a global army of passionate volunteers teaming up with professional astronomers to unlock the universe's secrets. And look, that's absolutely part of the story. It's real and it's powerful. But let's not kid ourselves. Let's not pretend this is all sunshine and collaboration. There's tension here. Real, palpable tension. Because opening the floodgates to citizen science means dealing with a whole lot of, well, everything it means dealing with false positives. With well-meaning amateurs who flag things that turn out to be nothing more than instrumental artifacts or random noise. It means contending with conspiracy theorists who see alien signals in every data glitch and who are absolutely convinced that scientists are part of a massive cover-up. And professional astronomers, understandably, worry about this a lot. The Royal Astronomical Society and other professional bodies have had long, intense debates about this very issue. On one hand, the benefits are undeniable. Citizen science dramatically reduces the backlog of data. It allows projects to process more information than would ever be possible with a small team of professionals. It engages the public, creates genuine enthusiasm for science, and inspires the next generation of researchers. It's a win-win. On the other hand, quality control is everything. A discovery isn't a discovery until it's been verified, cross-checked, and rigorously peer-reviewed. And that process takes time, expertise, and resources that are already stretched thin. False positives are a real, tangible problem. A citizen scientist flags an object as unusual. A professional team spends days or even weeks of valuable telescope time following up, only to determine it's a satellite trail, a cosmic ray hit on the detector, or just a statistical fluke. That's time that could have been spent chasing a genuine mystery. And when these false positives start piling up, astronomers can become understandably skeptical of citizen reports. The signal-to-noise ratio drops. Fatigue sets in. Then there's the human brain's greatest trick and its biggest flaw: confirmation bias. When people are looking for something specific, they have a nasty habit of finding it, even when it's not actually there. This happens to professionals too, but years of training and the brutal process of peer review provide powerful checks and balances. Amateurs operating without that structure might not have those same safeguards. They might see a pattern in random noise and convince themselves it's real, that it's a message, that it's a structure. This is how you get claims of alien megastructures around Tabby's star, or secret messages encoded in pulsar timing residuals. The brain is a pattern-matching machine, and sometimes it matches patterns that aren't there. Calibration and error margins are another huge hurdle. Professional astronomers spend years learning how to assess measurement uncertainty. They live and breathe statistics. They know when a signal is statistically significant and when it's just a blip, a 1 sigma fluctuation that's meaningless in the grand scheme of things. An amateur might not have that context. They might report a detection that looks impressive on a graph, but is actually just noise, leading to wild goose chases. And then there's the sheer bandwidth problem. If a citizen science project becomes too popular, if too many people start flagging too many things, the professional astronomers tasked with follow-up can become completely overwhelmed. They simply can't investigate everything. They have to prioritize, to make tough calls about which potential discoveries are worth their limited time. And that means some genuine, real discoveries might get missed simply because they're buried under a mountain of false alarms. But here's the thing: these problems aren't insurmountable. They're challenges, not deal. They are the messy, complicated reality of trying to do science in a more open, democratic way. And the solutions are just as powerful as the problems. Training protocols can make a world of difference. If citizen scientists are given clear guidance on how to assess data quality, how to recognize common artifacts, how to estimate uncertainty, the false positive rate plummets. Mentorship programs where experienced and knowledgeable amateurs guide newcomers can maintain high standards and build a community of expertise. tiered validation systems, where multiple independent volunteers must flag the same object before it gets escalated for professional follow-up, can effectively filter out the spurious detections and let the real gems shine through. The opportunities, when you get this right, are simply enormous. Crowdsourcing the hunt for anomalies means you can search larger datasets far more thoroughly than any algorithm could. Cross-checking by many independent human eyes dramatically reduces the chance that a real anomaly gets missed just because one person was having an off day. And diverse perspectives mean people from different backgrounds with different life experiences might notice patterns or connections that highly specialized professionals deep in their niche might completely overlook. Let's bring this back to 3E Atlas one more time. Could a citizen astronomer have flagged its nickel anomaly early? The spectral data is, for the most part, public. Anyone with the right software can download it and take a look. But spectroscopy is hard. It's not like looking at a pretty picture of a galaxy. It requires understanding line identifications, wavelength calibrations, signal-to-noise assessments, and a whole host of other technical details. It's not something you can do casually. But maybe, just maybe, with the right training, the right guidance, and a community of people working together, someone could have noticed that oddity, that missing iron line, before it made headlines in the scientific journals. The same goes for the water production rate. Comet light curves measurements of brightness over timer, often contributed by a network of dedicated amateur astronomers. If those amateurs had been looking at ultraviolet data from the Swift telescope, and if they'd been trained to recognize unusual activity patterns, they might have flagged 3E Atlas's superlinear brightening. They might have been the first to say, "This doesn't look like a normal comet," long before the professional surveys confirmed it was something truly special. The conclusion here isn't that we should replace professional astronomers with amateurs. That's absurd. The conclusion is that we desperately need both. We need professionals for their deep expertise, their theoretical frameworks, and their rigorous validation. And we need citizen scientists for their breadth of coverage, their fresh perspectives, and the sheer number of eyes they can bring to a problem. This isn't a competition, it's a partnership. And in the era of data deluge, where we're all drinking from a fire hose of cosmic information, it's not just a nice-to-have partnership, it's a necessary one if we're going to make sense of it all. October 2025 rolled in, and with it came something unusual. Not a comet, not a strange signal, but a simple, beautiful celestial alignment. The viewing conditions for two of our solar system's residents were absolutely perfect. Mercury, that fleet-footed, elusive innermost planet, swung into a prime evening apparition, hanging bright and high above the horizon after sunset, like a cosmic jewel. At the same time, Ceres, the largest object in the asteroid belt and a dwarf planet in its own right, reached opposition. That's astronomer speak for being directly opposite the sun in our sky, meaning it was at its absolute brightest and closest to Earth, a prime target for telescopes. On its own, this is just cool astronomy. A happy coincidence, a great time to be an amateur stargazer. But then, something else was happening in our skies. That weird, impossible interstellar comet, 3E Atlas, was still acting alive, still hemorrhaging water and glowing green. defying every rule we thought we knew. And on social media, the dots started getting connected. Mercury is visible. Ceres is visible. And now this bizarre, otherworldly comet is putting on the performance of a lifetime. Were they related? Was there some grand cosmic alignment happening right over our heads? Were the gravitational fields of the inner solar system somehow triggering or amplifying the comet's bizarre behavior? The theories started flying, each one more intricate than the last. Let's be crystal clear, right from the start, no, absolutely not. There is no connection, zero, zilch, nada. Mercury's orbit has about as much to do with an interstellar comet's outgassing as a butterfly flapping. Its wings in Brazil has to do with a snowstorm in Siberia. Ceres's position relative to Earth has zero influence on the complex chemistry happening billions of kilometers away. These are independent events, coincidentally visible at the same time, and nothing more. The gravitational influence of Mercury on an object in the outer solar system is essentially zero. Mercury is tiny, only slightly larger than our moon, and it's inconceivably far away. Ceres is even smaller and even less influential. The combined gravitational pull of every planet in our solar system couldn't significantly alter 3E Atlas's behavior at the distances we're observing it. The comet is doing what it's doing because of its own internal processes. The solar radiation it's bathing in and its own unique alien composition, not because of where Mercury happens to be in its orbit. But facts, as we all know, don't always stand a chance against a compelling narrative. The human brain craves stories. We are desperate for events to be connected because disconnected events feel random, chaotic, and ultimately meaningless. If the comet's strange activity is somehow linked to planetary positions, then there's order, there's predictability, there's a hidden design, a meaning to the madness. If they're unrelated, then we live in a universe where strange things just happen sometimes for no reason at all. And that's psychologically uncomfortable. This isn't a new phenomenon. This is hardwired into our DNA. We're pattern recognition machines, and it's a survival trait. Our ancient ancestors who noticed that certain patterns of berries led to sickness, and that specific animal tracks led to prey, were far more likely to survive than those who didn't notice the patterns. So, our brains are hypersensitive to finding connections, sometimes to the point where we find them where they don't exist. This is pareidolia on a cosmic scale. Pareidolia is seeing faces in clouds, hearing voices in the static of a radio. It's our incredible pattern detection software gone haywire, firing on all cylinders. And it happens with celestial events all the time. Ancient cultures saw omens in planetary alignments. When a comet appeared during a battle, it meant the gods were angry. When planets gathered in one part of the sky, it was seen as a signal of the birth or death of kings. We like to think we're more sophisticated now, but are we? Let's go back to 1910. That's the year Halley's Comet returned, swinging through the inner solar system on its 76-year orbit. And people were absolutely terrified. Astronomers, using the new tool of spectroscopy, had detected cyanogen, a toxic gas, in the comet's tail. The press, being the press, ran with it. Sensational headlines screamed from every newsstand. Comet's poisonous tail will pass over Earth. Panic ensued. people bought gas masks in record numbers. Some sealed their windows with towels and tape. There were even reports of suicides by people utterly convinced the comet would kill them all. Of course, nothing happened. The comet's tail is incredibly diffuse, basically a hard vacuum by terrestrial standards. The amount of cyanogen that actually reached Earth's atmosphere was negligible, completely undetectable. The comet posed zero threat. But the coincidence of the comet's appearance with other unrelated events, solar activity, political unrest in Europe, a few earthquakes here and there fueled the panic. People connected dots that had no business being connected. They created a narrative of doom, and their brains, desperate for a story, accepted it without question. We are seeing the exact same thing now with 3 Atlas. The comet is genuinely weird, genuinely anomalous. Mercury and Ceres happen to be visible at the same time, and suddenly people are constructing narratives. Maybe the comet is being awakened by some sort of solar system resonance. Maybe its trajectory is being subtly altered by gravitational perturbations we can't detect. Maybe this is all part of a larger, intricate pattern we don't yet understand. Confirmation bias magnifies this effect exponentially. Once you start looking for connections, you find them everywhere. Mercury was also visible during a previous comet discovery. Ceres was near opposition when another unusual object was detected. Never mind that Mercury is visible several times a year and Ceres reaches opposition annually. Never mind that unusual astronomical discoveries happen constantly. The brain conveniently filters out the non-coincidences and remembers only the ones that fit the compelling narrative and social media. Social media is the ultimate amplifier. In the old days, if you had a theory about planetary alignments affecting comets, you might tell your friends who would probably tell you it was nonsense, and that would be the end of it. Now, you post your theory online, and within minutes, you find a whole community of people who not only agree with you, but are ready to build on your ideas. You share links, images, and charts showing the alignments. Someone adds a new piece of evidence. Someone else shares it further. Before long, you have a full-blown alternative narrative, complete with its own jargon and experts, competing directly with the scientific explanation. The lesson here isn't that people are stupid or gullible. The lesson is that coincidences are powerful, and our brains simply aren't well calibrated to dismiss them. Statistically, with thousands of astronomical events happening all the time, some will coincide purely by chance, and those coincidences will feel meaningful, will feel important, even when they're not. This matters because it directly affects how people interpret genuine anomalies like 3 Atlas. If you're already primed to see cosmic conspiracies, to believe that alignments matter, then the comet's weird behavior becomes definitive proof of something larger. Maybe it's not a natural comet at all. Maybe it's artificial. Maybe it's responding to signals from the planets. Maybe it's part of some grand cosmic mechanism we don't understand. And that brings us to an even stranger, more unsettling chapter in this story: the machinery of hoaxes, conspiracy theories, and how humans turn scientific mysteries into cultural myths. Let's pivot from the cosmic scale for a moment and zoom in on something much closer to home, something that happened right here on Earth, in our own atmosphere. October 8th, 2025, Blue Origin mission NS-36. On paper, it was just another Tuesday for the private spaceflight company. 6 passengers, an 11-minute hop to the edge of space. One of them was a mystery flyer, a person whose name was kept under wraps until the capsule's wheels were safely back on the ground in the Texas desert. The launch went off without a hitch. The capsule crossed the Kármán line, the internationally recognized boundary of space. The passengers floated in microgravity, gawking at the curve of the Earth, and then descended gently under parachutes. Success, another flawless mission. The 15th crewed flight for their new Shepard rocket, routine. Almost. That's the official story, anyway. ABC News ran a brief segment. Medium published a short, perfunctory piece. A handful of space journalists, the ones who followed this stuff for a living, fired off a few tweets. The mystery passenger was revealed after landing some private individual who'd requested anonymity for the flight itself but was happy to be named afterward. Nothing unusual there. People with that kind of money pay for privacy all the time. But here's what's strange. Here's the detail that keeps nagging at anyone who follows the space industry closely. The little itch you can't scratch. The silence, the eerie, almost suffocating, vacuum-like lack of coverage. There were no viral videos, no trending hashtag, no celebrity reactions or memes or TikTok breakdowns from people who weren't even born when the first rockets flew. A human spaceflight, a commercial crew of 6 people leaving the planet, experiencing weightlessness, seeing the thin blue line of our atmosphere against the black of space, and returning safely. That is, by any objective measure, extraordinary. That should be headline news for days. It should be the kind of event that stops people in their tracks and makes them look up at the sky and wonder. Instead, the internet shrugged. Social media moved on within a few hours. The story vanished like a wisp of smoke, leaving no trace behind. Think about that for a moment. Let it really sink in. Why so little documentation? Blue Origin usually releases stunning, high-definition cabin footage. Beautiful, cinematic shots of passengers floating, laughing, pressing their faces against the thick windows like kids on a road trip. Where were those images? Why weren't they splashed across every news site and social media feed on the planet? Why didn't the mystery passengers reveal generate any real curiosity? Who were they? Why did they want to remain anonymous? These are natural, human questions, the kind of juicy details that usually fuel days of speculation and interest. Instead, nothing. Radio silence. It's as if the flight happened in a vacuum, not just of space, but of public attention. And that vacuum, that conspicuous absence, starts to feel like its own kind of presence. The silence becomes louder than any announcement could be. It becomes a blank space that your brain desperately wants to fill. You start to wonder. You start asking uncomfortable questions that feel paranoid even to yourself. Did this flight really happen exactly as described? Were there 6 passengers on board, or was the manifest different? Was the mystery passenger a real person, or just a narrative device to explain the lack of pre-flight publicity? Did the capsule actually launch on October 8th, or was this just repackaged footage from a previous flight with a new date slapped on it? These are the kinds of thoughts that get you labeled a conspiracy theorist. It's the kind of reasoning that sees shadows everywhere and trusts nothing. But sometimes the absence of evidence feels more significant than the evidence itself. When something should make a massive amount of noise and doesn't, you have to ask why. You have to wonder what you're not supposed to be seeing now. Let's contrast this with another Blue Origin flight from just 6 months earlier, in April 2025. That one didn't just make headlines. It exploded into public consciousness. Not because of a malfunction, but because of who was on board. Katy Perry, Gayle King, a crew of high-profile, A-list personalities, the first all-female crew for New Shepard. It was the kind of flight that was designed from the ground up to generate headlines, and boy, did it ever. But not the headlines Blue Origin was hoping for. Within hours of the livestream ending, social media erupted into a firestorm of conspiracy theories. People were absolutely convinced the flight was faked. They went full-on forensic, analyzing every single frame of footage, looking for inconsistencies. Hair behavior in zero gravity became a battleground. Does it float right? Does it move too stiffly? Is that real hair, or is it a wig, or worse, computer generated? The capsule hatch became another focal point. Someone claimed with absolute certainty that it opened differently than in previous flights. They posted side-by-side comparisons, drew arrows, circled supposedly anomalous details. Wasn't the latch on the other side last time? Didn't the door swing outward before? Why does this look different? Then came the really wild stuff. Claims of green screens, allegations that the passengers were filmed in a studio with fake windows showing pre-recorded Earth footage, accusations that their hands looked like mannequin hands, too smooth, too plastic, complaints about the absence of visible scorch marks on the capsule after every tiny detail, every pixel became irrefutable evidence of a massive high-tech deception. Journalists and experts patiently debunked the claims one by one. Hair behaves weirdly in microgravity because there's no gravity pulling it down, so it responds to the slightest air currents, static electricity, and random motion. The hatch mechanism is identical across all flights. It just looks different because of camera angles and lighting. Reflections in visors distort perspective. Scorch marks aren't always visible depending on landing site dust and camera resolution. But debunking didn't stop the theories. If anything, it fueled them. People who wanted to believe the flight was fake interpreted the debunking as part of the cover-up. They dug deeper, found more evidence, and built ever more elaborate models of how the hoax was perpetrated. The conspiracy became a self-sustaining ecosystem. So now we have 2 flights, 2 missions on the same rocket with the same basic profile, just 6 months apart. One generated a firestorm of attention, doubt, and intense scrutiny. The other barely made a sound. And you have to ask yourself, which is more suspicious? The flight that everyone thinks is fake, or the flight that no one seems to care about at all? It's a whole can of worms, and we're just starting to pry it open. The universe has a funny way of keeping us on our toes. It keeps throwing us curveballs, objects that don't fit, signals that make no sense, phenomena that violate our carefully constructed models of how things are supposed to work. And every single time, without fail, we do 2 things. First, we scramble like mad to understand the science behind it. Second, We project ourselves, our hopes, and our fears onto the mystery. We turn it into a mirror. Think about our first confirmed interstellar visitor back in 2017, a tumbling, reddish, elongated object that, as it left our solar system, started accelerating. Not by much, but it was measurable. That acceleration didn't fit a purely gravitational trajectory. Something was pushing it. Scientists proposed a bunch of natural explanations. Maybe it was releasing small amounts of invisible gas, a process called outgassing that created a tiny thrust like a weak comet. Or maybe it was a hydrogen iceberg, a frozen chunk of H2 that would sublimate into a gas we couldn't detect. Or maybe it was just a weirdly shaped fragment of a shattered planet. Its shape and spin creating radiation pressure effects, but a subset of people, including some very respected scientists, proposed something else entirely. What if Oumuamua was artificial? What if it was a light sail, a thin sheet of material designed to be pushed by starlight? That would explain the acceleration. And if it was artificial, maybe it was a probe from another civilization. Maybe it was exploring. Or maybe it was derelict, a piece of space junk from a long-dead alien society. A ghost ship adrift in the cosmic sea. The exact same thing happened with Tabby's star. KIC 8,462,852. A star in the Kepler field showing bizarre, deep and irregular dips in its brightness, sometimes dropping by 20% or more. No planet could do that. No planet is big enough to block that much light. And the dips didn't repeat with the regular clockwork of a planet's transit. Astronomers proposed dust clouds, swarms of comets, debris from a planetary collision. But one paper, half-jokingly, suggested an alien megastructure, a Dyson swarm, millions of solar panels or habitats orbiting the star, collecting its energy, which would block light irregularly as the structures moved. It fit the data, sort of, and the internet went wild, odd radio circles, fast radio bursts. 3 Atlas, every single mystery becomes a screen onto which we project our deepest existential questions. Are we alone? Is the universe an indifferent, random place, or is it intentional? Are there others out there? And if so, are they like us, or are they incomprehensibly alien? The psychology here is incredibly powerful. Pareidolia, that tendency to see patterns in randomness, is a huge part of it. We see faces in clouds, hear voices in white noise, and see intelligence in astronomical anomalies. It's not stupidity. It's the way our brains are wired. We are pattern recognition engines, and we are evolutionarily biased toward false positives. It was better for our ancestors to mistake a shadow for a predator than to mistake a predator for a shadow. That survival instinct is still with us. There's also a profound existential longing. We want contact. We desperately want to know that we're not the only sparks of consciousness in a vast, cold, and seemingly empty universe. Every anomaly is a chance, a possibility, a door that might open onto something extraordinary. And so we push on those doors, and we do it hard. 3 Atlas is a perfect mirror. In its glowing green coma, we see reflected our own insatiable curiosity, our hunger for meaning, our hope that the universe is stranger and more wondrous than our limited imaginations can conceive. And maybe it is. Maybe one day we'll find something genuinely inexplicable. Something that forces us to rewrite the laws of physics or accept the staggering reality that we are not, and have never been, alone. But that day hasn't come yet. For now, we have a comet. A weird comet, a fascinating comet, a comet that is stretching our understanding to its absolute limits, but still probably just a comet. And that's enough. Because even natural mysteries are extraordinary. The fact that a chunk of ice and rock from another star system, billions of years old, can sail into our neighborhood and start doing things we've never seen before is, in itself, one of the most incredible stories we could ever hope to witness. The real danger isn't in wondering if it's aliens. The real danger is in losing our sense of wonder if it turns out not to be. The real challenge is to remain fascinated by the natural world even when it refuses to conform to our expectations. The universe doesn't owe us easy answers or revolutionary discoveries. It just is. And our job is to look, to learn, and to appreciate the mystery for what it is, a chance to learn something new. 3 Atlas is a mirror. It reflects our science, our biases, our hopes, and our fears. It reminds us that we are creatures of story, and that we will always try to fit the strange and unknown into the narratives we already understand. But it also reminds us that sometimes the story is bigger than we are. Sometimes the universe has a tale to tell that we haven't even learned the language for yet. And in those moments, the best thing we can do is listen. Imagine the galaxy not as an empty void, but as a vast, ancient library. Not a library of books made of paper and ink, but a library of objects. Comets, asteroids, rogue planets ejected during the chaotic, violent formation of their planetary systems and flung into the endless dark between the stars. Each of these objects is a message in a bottle, a time capsule carrying a complete inventory of the star system where it was born. And occasionally, by sheer, mind-boggling chance, one of those bottles washes up on our cosmic shore. That's what interstellar objects are. They're postcards from alien systems, not alien in the sense of little green men, but alien in the truest sense of the word, foreign, different, formed under conditions and in environments that are nothing like our own little corner of the Milky Way. Every single one we detect is a data point, a sample of one. And with enough samples, we can start to build a statistical understanding of the incredible diversity of planetary system chemistries across the galaxy. Our solar system's comets, for all their individual quirks, are relatively uniform. They're all part of the same extended family. They formed in the same protoplanetary disk from the same well-mixed cloud of gas and dust, under the radiation field of the same star. Sure, they vary. Some are richer in carbon monoxide, some are more water-heavy, depending on exactly where in the disk they formed and what temperatures they experienced over billions of years. But fundamentally, they're siblings. They share the same DNA. Interstellar comets are strangers. They're the exchange students who show up from a school across the country, speaking a different dialect with different stories, different clothes, and different ways of looking at the world. They formed elsewhere under different stars, in disks with different compositions, different temperatures, and different dynamical environments. And so far, every single one we've seen has been wildly, fundamentally different. Let's recap the big 3 to to see what I mean. First, there was Almu, dry as a bone, non-outgassing, shaped like a cigar or a pancake, and accelerating for reasons we still can't fully explain. It didn't look like our comets. It didn't act like our comets. If it was a comet at all, it was a type we'd never encountered, a category of one. Then came to I Borisov. This one was much more familiar at first glance. It was active, it had a coma and a tail. It behaved like a comet should. But when we looked closer, we found it was incredibly rich in carbon monoxide, much more so than most of our comets. This suggested it formed in a much colder environment than most of the objects in our solar system. It looked familiar, but it was subtly off, like listening to a familiar song played in a weird key dot. And now we have three atlas, water and carbon, dioxide gushing at distances where neither should be active, nickel without iron, cyanide appearing late in the game. Nothing about its behavior fits our experience or our models. It's not speaking a different dialect. It's speaking a language we barely recognize, with grammar and vocabulary that seem to defy translation. Three objects, three wildly different chemistries, three completely different stories. If we dare to extrapolate, if we assume these three are even remotely representative of the broader population of interstellar objects, then the diversity of cometary compositions in the galaxy is absolutely staggering. It suggests that not all planetary systems produce comets like ours. In fact, maybe most don't. Maybe our solar system is the odd one out. Think about the possibilities. In some systems, comets might be dominated by nitrogen ice, like the surface of Pluto. In others, methane might be the primary volatile, the main driver of activity. In systems with more massive, hotter stars, the snow line, the distance from the star where water ice can condense and freezes much farther out. So, comets, they might form in colder, more distant regions and carry completely different volatile mixes. In systems where giant planets like Jupiter migrated inward or outward early on, the entire disk gets stirred up like a cosmic cocktail shaker, mixing materials from different temperature zones and creating comets with bizarre, hybrid compositions. Could some comets carry molecules we've never even seen before? Molecules that are thermodynamically possible but require formation pathways that simply don't exist in our solar system. Exotic organics, strange ices, compounds that would make a chemist's eyes light up with pure, unadulterated joy. Probably, the universe is big, and it's had billions of years and trillions of star systems to run the experiment. Nature explores every possible corner of the chemical space, and some of the results have to be strange. Now, let's take this a step further and revisit the panspermia idea, but from a different angle. If life as we know it requires certain chemical building blocks, water, organics, phosphorus, nitrogen, sulfur-then comets that lack those ingredients are for all intents and purposes sterile. They can't seed life. They can't deliver the prebiotic chemistry needed to get the party started on a young planet. Maybe many, or even most, interstellar comets are like that. Maybe Oumuamua was just a lifeless rock tumbling through the void, carrying nothing more interesting than some unusual minerals. But if even a small fraction of comets carry the right chemical recipe, that fraction is cosmically important. Because comets are galactic wanderers. They travel between stars, They cross light years over immense timescales, and if they carry organic molecules, amino acids, maybe even dormant microbes shielded deep inside their cores, then the building blocks of life can spread across the galaxy like a cosmic contagion. 3 Atlas, with its water, its organics, its cyanide, has the right ingredients. Not life, almost certainly not, but the chemistry that could lead to life if delivered to the right planet at the right time. Every interstellar object we detect expands our sample size. Right now, we have 3. In 10 years, thanks to new observatories like Vera Rubin, we might have dozens. In 50 years, we could have hundreds. And with each one, we'll measure its composition, its trajectory, its activity patterns. We'll build a statistical understanding of what's really out there. Maybe we'll find that water-rich comets are common, that most planetary systems produce them. Or maybe we'll find the opposite, that our solar system is the weirdo, and that water-rich comets are rare, while most systems produce dry, carbon-rich bodies instead. Either answer is fascinating, and maybe, just maybe, we'll find a comet with clear molecules that are incredibly difficult to explain without invoking biology. Phospholipids, complex organics with chirality, a handedness that life often prefers. Isotope ratios that scream of active metabolism. That would be the revolution to end all revolutions. That would tell us, once and for all, that life arose elsewhere. That biochemistry isn't unique to Earth. We haven't found that yet. 3 Atlas isn't carrying life as far as we can tell. But it is carrying information. And in science, information is the most valuable currency in the universe. Every interstellar visitor is a gift, a free sample delivered right to our doorstep. All we have to do is look closely enough to read the label. Let's circle back to that nickel anomaly one more time, because it's not just a quirky detail or a fun fact for a trivia night. It's a clue, a chemical fingerprint, and fingerprints, as any detective will tell you, don't just tell you who someone is. They tell you where they've been. In this case, the nickel in 3 Atlas is telling a story that stretches back to the violent death of a star that died billions of years ago. In a part of the galaxy we may never see, dot stars are the universe's ultimate alchemists. In their cores, nuclear fusion takes the simplest elements, hydrogen and helium, and forges them into heavier ones, carbon, nitrogen, oxygen, silicon, sulfur, and iron. But the process stops there for most stars. To create elements heavier than iron, you need something much more violent. You need a supernova, when a massive star implodes and then explodes in one of the most energetic events in the cosmos. The blast wave creates elements like nickel, gold, platinum, and uranium, scattering them into the surrounding space like cosmic shrapnel. These newly forged elements get mixed into vast clouds of gas and dust, and eventually, millions or billions of years later, those clouds collapse to form new stars and new planetary systems. But here's the crucial part. Not all stars have the same recipe. The abundance of heavy elements, what astronomers call metallicity, varies wildly from star to star. Young stars that formed recently from gas enriched by generations of supernova have high metallicity. They're rich in the good stuff. Older stars that formed when the galaxy was young, before many supernovae had had a chance to see the interstellar medium have low metallicity. They're running on a leaner diet. Nickel and iron are both produced in supernova, but in slightly different amounts, depending on the type of explosion. A type Ia supernova, where a white dwarf star accretes matter from a companion and then detonates, produces different ratios of nickel to iron than a core collapse supernova, where a massive star dies in a cataclysmic collapse. If 3E Atlas formed in a system whose birth gas cloud was enriched by an unusual mix of these different types of supernova, its nickel to urine ratio could be permanently skewed. Now, remember, we think 3E Atlas might have come from the thick disk, that ancient population of older stars. Thick disk stars have lower overall metallicity, but the specific ratios of different heavy elements can vary in ways that tell a story about the galaxy's past. If the nickel decoupling we're seeing in 3A Atlas, the nickel without its iron partner, is a direct reflection of its parent star's unique composition, then that comet isn't just a space rock. It's a tracer. It's a messenger. It's telling us about galactic chemical evolution in ways we can't easily access any other way. Because here's the thing, we can analyze the atmospheres of stars we can measure their iron, their nickel, their everything from light years away. But stars are far away, and we can only study a tiny fraction of them in the kind of detail we'd need. More importantly, we can't study stars that no longer exist. Stars that lived and died billions of years ago, leaving behind only the chemical remnants of their lives. But comets from those long-dead systems, they are time capsules. They are physical archives. They preserve the chemical conditions of their birth, frozen in time, waiting for someone to read them. If we could get our hands on a piece of 3E Atlas, if we could send a probe to intercept it, land on it, drill into its surface, and bring back a sample to analyze in a laboratory on Earth, we would be holding a piece of a star system that might be billions of years old and thousands of light years away. We would be reading history written in atoms. We could measure the isotope ratios of the nickel, which could tell us precisely what kind of supernova created it. We could study the mineral structures, which could tell us about the temperatures and pressures it experienced. It would be a direct, tangible link to a part of the galaxy's past that is otherwise lost to us forever. Now, let's entertain a speculative idea, a fringe idea, but one that gets discussed in certain scientific and sci-fi circles. Could metal anomalies like a high nickel content be signatures of processed material? Not natural processing like thermal metamorphism, but technological processing. If an advanced civilization were mining asteroids, refining metals, building structures in space, they would generate waste. Slag, tailings, exhaust. That material would have unusual elemental ratios because industrial processes are selective. You extract iron for construction, maybe, and discard the nickel-rich residue. Or you use nickel for some specific high-tech application and dump everything else. If a comet formed in a debris disk that contained this kind of industrial waste, it might incorporate those anomalous metals into its structure, and then millions or billions of years later, that comet gets ejected from its system, wanders the galaxy, and arrives in our solar system. We detect the nickel anomaly and scratch our heads, trying to come up with a natural explanation that, to be absolutely crystal clear, there is zero evidence that 3 Atlas is artificial or contaminated by tech designatures. None. The idea is speculative to the point of being science fiction. Most scientists dismiss it outright, and they should. The burden of proof is immense, but it's not physically impossible. And in the absence of a clear, natural explanation for the nickel-ion decoupling, even wild ideas get a hearing in the back of our minds. The more likely explanation is some kind of prosaic, albeit exotic, chemistry. Nickel trapped in organometallic compounds. Fractionation during the disk's formation. Some process we haven't thought of yet that operates under conditions common in other star systems but are rare or absent in our own. But here's what truly excites me about this. Every comet carries a chemical signature, a barcode written in elements and isotopes. If we can build a library of those signatures, if we can catalog the compositions of dozens or hundreds of interstellar objects, we can start to map the galaxy itself. Imagine a future where interstellar objects are so common, where our detection technology is so good that we're cataloging them by the dozens every year. Each one gets a full spectroscopic analysis. Each one's trajectory gets traced back as far as possible. Each one's composition gets added to a massive, ever-growing database. Eventually, patterns would emerge. We might find that comets coming from the direction of the galactic center have systematically different abundances than those coming from the outer halo. We might find that comets from the thick disk show age-related signatures that are distinct from those in the thin disk. We could use comets as tracers of galactic structure and evolution, like forensic investigators using trace evidence to map out a crime scene. 3 Atlas is the beginning of that library. One entry, one data point, but it's a start. And the nickel, that strange, decoupled, standalone nickel, is a reminder that every data point has a story. Every element ratio is a clue. And if we're patient, if we're careful, if we keep looking, we can read those stories and piece together the history of the galaxy itself, one wandering comet at a time. So far, we've confirmed 3 interstellar visitors in the span of just 7 years. Oumuamua, 2 Borizovi, and now 3. Atlas. On a cosmic timescale, that's a blink of an eye. 3 objects might not sound like a lot, but it's enough data to do some serious statistical back-of-the-envelope math. It's enough to make a chilling, yet exhilarating, estimation of how many more of these things are out there, passing through our solar system right now, completely unseen. Astronomers have run the numbers. They've taken the detection rates, factored in the limited sky coverage of our surveys, and accounted for the observed properties of these 3 objects. Their conclusion is staggering. At any given moment, there are probably several interstellar objects within Jupiter's orbit alone. They're small, they're dark, they're moving incredibly fast, and they're invisible to the vast majority of our telescopes. We've only detected 3 because we got lucky. Ridiculously lucky, because they passed close enough to Earth, or were bright enough, or happened to be in the right patch of sky when the right telescope was looking. So, the real question is, how many do we miss? Hundreds? Thousands? For every interstellar comet we detect, dozens, maybe even hundreds, probably pass through unnoticed. Some are simply too faint, too small to catch the light of our sun. Some move too fast across the sky for our telescopes to track and follow up on. Some appear in parts of the sky we aren't monitoring, or at times when our instruments are pointed elsewhere. The truth is, our solar system is probably being traversed by a constant, unseen stream of these cosmic nomads, but that's changing fast. The era of accidentally stumbling upon these objects is coming to an end. New surveys are coming online with unprecedented sensitivity and sky coverage, and they are about to flip the switch from rare curiosity to common occurrence. The star of this new show is the Rubin Observatory, currently under construction in the mountains of Chile. When it becomes operational, it will fundamentally change the game. This isn't just another telescope. It's a cosmic motion picture machine. It will scan the entire visible sky every few nights, imaging everything down to incredibly faint magnitudes. With a camera the size of a car, it will detect asteroids, comets, supernova, anything that moves or changes brightness. And it will be exceptionally good at finding interstellar objects. Current estimates suggest that the Rubin Observatory could detect one interstellar object per month, maybe even more. That's a minimum of 12 per year. In a decade, we'd have over 120 confirmed interstellar visitors. That's not a sample of one. That's a statistical population. That's enough data to start drawing real, robust conclusions about their compositions, their origins, and their diversity. And it's not just optical telescopes. The Square Kilometre Array, SKA, a colossal radio telescope network being built across Australia and South Africa, will also be a game changer. Radio observations can detect molecular emissions from comets, even faint ones that are invisible in optical light. The SCAR could spot interstellar comets that are dark, dormant, or shrouded in dust, revealing them through the faint radio whispers of their chemistry. Space-based ultraviolet and infrared telescopes will add another layer, catching comets that are active but whose light is obscured or blocked at optical wavelengths. Every new instrument, every new technological leap expands our detection capability. Our ability to see these faint, fast wanderers is growing exponentially, but detecting is only half the battle. Studying them is the other, much harder half. Interstellar objects move fast. We're talking tens of kilometers per second relative to the Sun. By the time we spot them, calculate their orbits, and plan follow-up observations with other telescopes, they're often already on their way out. Oumuamua was on its exit trajectory when we discovered it. We got one good, long look, and then it faded into the distance, too faint to observe, taking its secrets with it. To Borisov, we caught inbound, which was the ideal scenario. It gave us months to study it. Telescopes all over the world pointed at it. We got spectra, light curves, detailed observations of every kind. 3E Atlas we also caught relatively early, so we're getting good data. But soon it will reach perihelion, its closest point to the Sun, swing around our star and head back into the darkness. And then it will be gone forever. Unless we intercept it, this is where science fiction starts to bleed into reality. There are serious, well-funded proposals for interstellar object intercept missions. Imagine a spacecraft designed to launch quickly, accelerate with incredible power, and rendezvous with an interstellar visitor while it's still in the inner solar system. The technical challenges are, to put it mildly, enormous. You'd need a spacecraft on standby, ready to launch on short notice. You'd need propulsion systems far beyond what we currently use for deep space. Missions to match the object's blistering velocity. And you'd need a suite of instruments capable of analyzing composition, structure, and maybe even collecting a sample on the fly. But the scientific payoff would be, without exaggeration, incalculable. Imagine landing on an interstellar comet. Imagine drilling into its surface, collecting pristine ice and rock from another star system, and bringing it back to Earth for analysis in the cleanest, most advanced laboratories we can build. The science we could do with that material is almost beyond imagination. We could determine precise isotope ratios, which tell you about the specific nuclear processes that cooked up the elements in its parent star. We could analyze complex organic molecules in ways you simply can't do remotely with a telescope. We could search for amino acids, for the building blocks of proteins, for prebiotic chemistry. And if we were the luckiest species in the galaxy, we might even search for fossilized microbes. Even if we don't find life, we would learn about the chemistry of alien planetary systems in exquisite, breathtaking detail. Every molecule, every mineral, every isotope would be a clue, a piece of a puzzle that spans light years and eons. Some scientists are already planning these missions. Concepts exist, budgets are being proposed. This isn't just a dream. It's engineering. Hard, expensive, long-term engineering. But it is doable. In 50 years, maybe 100, we might have catalogued hundreds of interstellar objects. We might have intercepted a dozen. We might have returned samples from half a dozen. And with that data, we would have a comprehensive understanding of galactic comet populations, planetary system diversity, and maybe, just maybe, the prevalence of life's building blocks across the Milky Way. 3E Atlas is a preview, a glimpse of what's possible. It's showing us that interstellar comets aren't just rare curiosities. They're common, they're everywhere, and they're carrying information we are desperate to understand. The unseen population is out there tumbling through the dark, waiting for us to find them. And we will, one by one, will catalog them, study them, and piece together the puzzle of how planetary systems form, how chemistry varies across the galaxy, and how common the conditions for life truly are. Let's zoom out, way, way out. Let's pull back from the strange case of 3E Atlas and look at the bigger picture. Because this comet isn't the only weird thing happening in astronomy right now. Not by a long shot. In fact, it feels like we're living in a golden age of cosmic oddities. A time when the universe is throwing so many curveballs at us that we're starting to wonder if we've misunderstood the rules of the game entirely. Let's make a list, just to get a sense of the scale of it all. We have odd radio circles, ORCs, those mysterious, gigantic rings of radio emission whose origin is still completely unknown. We have fast radio bursts, FRBs, millisecond duration, pulses of radio energy coming from distant galaxies whose mechanism is still hotly debated. We have Tabby's star with its bizarre, deep, and irregular dimming patterns that still aren't fully explained, even years after the initial hype died down. We have Oumuamua, the interstellar object with its anomalous acceleration and weird shape. And now we have 3E Atlas, a comet with impossible water production and metal anomalies that defy everything we thought we knew. and those are just the high-profile, headline-grabbing cases. Dig a little deeper, and you'll find dozens, maybe hundreds, of lesser-known anomalies. Transient events that don't fit into any known category. Spectral features that shouldn't exist. Objects moving in ways that defy easy explanation. The universe, it seems, is full of things that make astronomers scratch their heads and say, "Huh, and this is new." For most of the 20th century, astronomy was a data-starved science. You pointed a telescope at something, took a photograph or a spectrum, and then you spent months, sometimes years, carefully analyzing that single piece of data. Discoveries were rare, celebrated events. Anomalies were even rarer. When something truly weird showed up, it got intense. Focused scrutiny, because there wasn't much else competing for the community's attention. Now, we're drowning in data. We're in the middle of a data tsunami. Automated surveys like the Zwicky Transient Facility and the upcoming Vera Rubin Observatory generate terabytes of information every single night. All sky surveys catalog billions of objects. Gravitational wave detectors like LIGO and Virgo record the mergers of black holes and neutron stars in real time. Radio telescope arrays scan the sky continuously. 24/7, we are detecting more stuff, more phenomena, more things than we can possibly follow up on. And with this high volume of data comes a high rate of anomalies. If you look at 1 billion objects, even if only 1 in 1,000,000 is genuinely weird, that's still 1,000 anomalies. Most of them, of course, will turn out to be instrumental artifacts, data glitches, or but some of them will be real. And sorting through the signal to find the real anomalies in all that noise takes an immense amount of time and effort. We are in an era where anomalies are outpacing our theories. We are finding things faster than we can explain them. And that's both incredibly exciting and, in a way, dangerous. It's exciting because new, unexplained phenomena are where scientific breakthroughs are born. The discovery of pulsars, of gamma-ray bursts, of gravitational waves, all of them started with an unexplained observation that made no sense. Anomalies are the sharp edges of knowledge. The places where our maps of reality have blank spaces labeled "Here be dragons." Pushing into those spaces is how science grows, but it's also dangerous, because hype cycles can spin completely out of control. Every anomaly gets hyped as potentially revolutionary. Is it an alien megastructure, a warp drive signature, a wormhole, evidence of dark matter interactions? The media loves it. The public eats it up. And then, 9 times out of 10, the anomaly gets explained by something much more prosaic. Dust clouds, instrumental noise, a misidentified known object, a statistical fluke. The danger here is credibility erosion. The public hears it could be aliens 12 times, and then 12 times the answer turns out to be just dust. After a while, people stop trusting scientists. They start to think that science is just wild speculation dressed up in fancy language. Or worse, they double down on the alien explanation, deciding that scientists are either incompetent or actively involved in a cover-up. Tabby, single quotes as star, is the perfect cautionary tale here. When the alien megastructure hypothesis first made headlines, the public latched onto it with a ferocity that was astonishing. Social media exploded. News articles ran with the most sensational angle. And when follow-up observations showed wavelength-dependent dimming, which strongly indicated the culprit was dust, not solid artificial structures, there was a backlash. Some people accepted the explanation. Others insisted the scientists were wrong, or lying, or part of a conspiracy to hide the truth. But here's the thing that gets lost in the noise. Tabby's star is still interesting. The dust explanation doesn't fully account for all the long-term observations. The star shows complex variability that is still not perfectly understood. It's a weird star, possibly surrounded by a complex debris disk from a planetary collision, possibly doing something we don't entirely understand yet. It's still science. It's still a valuable mystery. It's just not aliens. The lesson is that anomalies are opportunities. They push us to refine our models, to consider new mechanisms, to challenge our most fundamental assumptions. Even when they don't revolutionize physics, they advance it, forcing us to look closer, to measure more precisely, to think more creatively. Oumuamua's acceleration, even if it turns out to be just outgassing from an exotic ice, forced cometary scientists to think harder about sublimation at extremely low temperatures, about surface properties, about the kinds of chemistry that might be possible in the deep freeze of interstellar space. That's progress. That's science working as it should. 3 Atlas is another one of these opportunities. Its water production challenges our understanding of volatile activation at great distances. Its nickel anomaly forces us to think about metal chemistry in comets, something we've largely ignored because our own comets don't show strong metal emissions. Its carbon dioxide dominance opens up a whole new set of questions about the conditions in protoplanetary disks around other stars. When you stack enough of these anomalies together, patterns can start to emerge. Maybe ORCs and FRBs are related, both involving energetic outflows from galactic centers. Maybe interstellar objects like Oumuamua and 3A Atlas represent distinct populations with completely different formation mechanisms. Maybe the entire transient zoo of astronomical phenomena is telling us something fundamental about how energetic, how dynamic, how violent the universe truly is on scales we can barely comprehend, or maybe not. Maybe they're all unrelated, individual quirks that just happen to be occurring in the same few decades because we finally have the technology to detect them. Either answer is informative. The key is to maintain a sense of skepticism and wonder simultaneously. You can be incredibly excited about an anomaly without immediately claiming it rewrites physics. You can investigate weird, out-there possibilities without becoming wedded to them. You can change your mind when new evidence arrives. This is where good science communication matters more than ever. When reporting on 3 Atlas, responsible journalists and scientists should say, "This comet is behaving unusually. We're investigating several possible explanations. Here's what we know so far, and here's what we don't know. Not alien comet violates laws of physics, not scientists baffled by impossible objects, but nuance doesn't generate clicks. Careful, measured language doesn't go viral. And so the hype machine grinds on, turning every anomaly into a potential revolution, setting up a wave of disappointment when the mundane, but still fascinating, explanation eventually arrives. The solution isn't to stop reporting on anomalies. The solution is to be honest about uncertainty, to present multiple hypotheses to update the public when the evidence changes. Treat the public like adults who can handle ambiguity because they can. Most people understand that science is a process, that answers evolve, and that we don't know yet is a perfectly acceptable and often exciting response. 3 Atlas is one anomaly in a whole stack of them. It's important, it's fascinating, but it's not proof of anything yet. It's a data point, a mystery, an opportunity to learn. And whether it ends up being a weird natural comet or something we've never seen before, the process of studying it, of testing hypotheses, of ruling out explanations one by one, is where the real value lies. That process is science. And science, when done honestly and with humility, is one of humanity's greatest achievements, especially when it's grappling with things it doesn't yet understand. So here we are, thousands of words deep into the unfolding mystery of 3 Atlas. We've got an interstellar comet that's hemorrhaging water into the void, where water should be frozen solid. We've got it glowing an eerie green with nickel and cyanide, elements that are either acting strangely or showing up in the wrong proportions. We've seen it switch on and off like it's following some kind of pre-programmed schedule. We've traced its origins back to a population of ancient stars that predate our own sun. We've even entertained the wild notion that it might be a cosmic cargo ship, carrying the building blocks of life, the question that hangs in the air, the one that underpins all the speculation and the wonder is simple and profound. Is it alive? In the poetic sense, the romantic sense, maybe. It's dynamic, it's changing, it's actively responding to its environment in ways that feel complex and almost intentional. It's active when it should be dormant. It behaves in ways that feel purposeful, even though we know on an intellectual level that it's all driven by the impersonal, unfeeling laws of physics and chemistry, not by any form of consciousness or intention, but alive in the literal, biological sense. Almost certainly not. Let's be very clear about that. There is no evidence of biology here, not a shred. No metabolic processes, no reproduction, no information storage and transfer, no cellular structure. None of the hallmarks of life as we understand it. 3 Atlas is, in all likelihood, exactly what it appears to be, a complex, porous rock covered in exotic ices, being heated by sunlight and releasing gas and dust according to the physical laws that govern all matter in our universe. And yet, those physical laws are producing something we've never seen before. Water sublimation at unprecedented distances from the sun, nickel without iron, a carbon dioxide-dominated coma, switch-on behavior that suggests a complex internal structure or exotic ice compositions we've never encountered. Every new observation adds another layer to the puzzle, another piece to a jigsaw that doesn't seem to have a picture on the box dot. So, what is it? The most likely explanation, the one that requires the fewest logical leaps, is that 3 Atlas is a natural comet that formed under conditions very, very different from those in our solar system. Maybe it formed farther from its star, in a much colder region of its protoplanetary disk, where carbon dioxide ice was more abundant than water ice. Maybe its parent star had an unusual composition, leading to the weird metal ratios we're seeing. Maybe billions of years of relentless space weathering in the harsh environment between stars has altered its surface chemistry in ways we can't yet model. The organometallic hypothesis is particularly intriguing. If nickel got incorporated into volatile compounds like nickel carbonyl during its formation, that could elegantly explain the decoupled emissions we're seeing. It would require a very specific set of chemical conditions to be present in the comet's birthplace. But nothing that is physically impossible, just unusual and unexpected. The thick disk origin is also a compelling piece of the puzzle. If 3E Atlas is truly 7 billion years old, if it carries isotopic signatures from an earlier, more primitive era of galactic chemistry that could explain some of its oddities, ancient ice, ancient chemistry, ancient minerals, all preserved in the deep freeze of interstellar space for eons, and now being revealed as the comet makes its fiery, untimely pass by our sun. Could it be artificial? Could it be a probe, a derelict spacecraft, some kind of technological artifact left behind by a long-gone civilization? The evidence we have right now simply doesn't support that. Nothing about 3E Atlas requires a technological explanation. Everything we're observing can be explained, or at least plausibly hypothesized, by natural processes. Invoking aliens is, as the scientific principle of Occam's razor suggests, an unnecessary complication. It's an answer that creates more questions than it answers. But let's entertain the thought for just a moment. Not as a likely scenario, but as a fascinating intellectual exercise. If you wanted to design something that would survive an interstellar journey that could last millions or billions of years and still be detectable when it arrived in another star system, how would you do it? You probably wouldn't build a sleek, metallic starship like in the movies. You'd use the materials at hand. You'd probably use a comet-like object as a natural shell, protecting your payload with kilometers of ice and rock, the best radiation shielding in the universe. You might include unusual chemical signatures, markers that would stand out to any civilization advanced enough to analyze the object's spectrum. You'd let natural solar heating reveal those markers as the object approached its destination. This is pure, unadulterated speculation. There is no evidence for it. But it's worth noting that if we ever do encounter an artificial interstellar object, it might not look artificial at first glance. It might look like a comet. A weird comet, sure, but one that could be explained as natural until you dug much deeper. 3E Atlas isn't that. Probably, almost certainly. But the fact that we're even asking the question tells you something important. It tells you that this comet is strange enough to stretch our imaginations to their breaking point, to make us wonder, to force us to consider possibilities we would normally dismiss without a second thought. And maybe that's the real value here. Not whether 3E Atlas is natural or artificial, not whether its chemistry is merely unusual or genuinely revolutionary, but that it makes us think. It makes us question our most basic assumptions about what is normal in the cosmos. It reminds us that the universe is bigger and stranger than our little corner of it, that nature has had billions of years and trillions of star systems to explore the full range of what's chemically and physically possible, and that we, as a species, have barely begun to survey what's out there. Every interstellar visitor is a challenge. It challenges our models, our theories, our sense of cosmic familiarity, and challenges are how we grow. Oumuamua challenged our understanding of cometary activity. 2I Borisov challenged our assumptions about carbon monoxide abundances. 3E Atlas is challenging everything at once: volatile budgets, metal chemistry, activity distances, compositional diversity. It's a full frontal assault on our complacency. The next steps are clear. We watch 3E Atlas as it approaches perihelion. We measure everything we possibly can: spectra, light curves, gas production rates, dust-to-gas ratios. We look for new emission lines to appear. We watch to see if iron finally shows up, or if the nickel anomaly persists all the way to the sun. We compare our observations to our models. We refine those models. We generate new predictions, and we test them again. And we prepare for the next interstellar visitor, because there will be another. And another. The galaxy is full of these wanderers, and our detection technology is getting better, faster, and more sensitive every single year. Each one will be a new puzzle, a new set of clues, a new window into how planetary systems form and evolve across the staggering diversity of stellar environments in our galaxy. Maybe one day we'll intercept one. We'll land on it, drill into it, and bring back a sample. We'll analyze its isotopes in terrestrial laboratories, study its minerals under electron microscopes, search its organic inventory for prebiotic molecules, and we'll learn things we can't even imagine right now. Until then, we watch, we measure, we wonder, because that's what humans do. We look at the universe and we ask questions. Why is that comet active so far from the sun? Where did it come from? What can it teach us about our place in the cosmos? The questions themselves are valuable even before we have answers, because questions are how exploration begins. 3 Atlas came from somewhere out there, across light years and billions of years, carrying a message written in water and nickel and cyanide. We didn't ask for this message. We don't know what it says yet. But we're listening. We're watching. We're learning. And in that act of learning, in that stubborn, beautiful insistence on understanding, we find something that might be the closest thing to alive in this whole story. Not the comet US. Curious, wondering, reaching out to touch something that came from impossibly far away, trying to read a letter from another world. The universe keeps sending these letters. Cosmic postcards, messages in bottles, visitors from the dark. And every time one arrives, we're reminded that we live in a vast, ancient, and incomprehensibly rich cosmos. A cosmos that will forever outpace our understanding, that will forever surprise us, and that will forever offer up new mysteries that humble us and ignite our curiosity in equal measure. 3E Atlas is one such mystery, one comet in an infinite sky. But it's our mystery now, and whether it's just a chunk of ancient ice or something more, whether its secrets yield easily or resist our efforts for decades, we'll keep looking. We'll keep asking. We'll keep listening for what the universe is trying to tell us, because that's what it means to be human. To see something strange in the night sky and to refuse to look away, to demand answers even when the universe stays silent, to find wonder in a spray of water molecules 40 kilograms at a time, in the green glow of nickel that shouldn't be there, in a trajectory that points back toward stars we will never reach. We are small, the universe is vast, but between us and that vastness, between our telescopes and those distant comets, between our questions and whatever answers we might eventually find, there's a conversation happening. It's a slow, deliberate conversation that spans centuries and light years, written in photons and spectral lines and orbital mechanics. 3 Atlas spoke. We heard it, and we're still listening, straining to understand what it might say next. This cosmic conversation isn't a one-way street. It's a dialogue that stretches back to the very first time a human looked up at the night sky and felt a sense of awe. It's a dialogue that Galileo had when he first pointed his telescope at Jupiter and saw its moons, shattering the idea that Earth was the center of everything. It's a dialogue that Edwin Hubble had when he measured the distance to the Andromeda Nebula and realized it was an entire galaxy, revealing the true scale of the cosmos. It's a dialogue that Jocelyn Bell Bernal had when she saw the regular, repeating pulses of a pulsar, a signal so precise it was initially nicknamed LGM for Little Green Men. Each of these moments was a new sentence in the ongoing story. Each discovery was a new word added to our cosmic vocabulary, and 3 Atlas is just the latest chapter. It's a new word, a new concept, a new piece of the puzzle that doesn't quite fit with the pieces we already have. And that's what makes it so valuable. It forces us to expand our vocabulary, to learn a new dialect of the language of the universe. Think about the language we're using to describe it. Impossible water production, nickel without iron, superlinear brightening. These are phrases we're inventing on the fly because our old language, our old models, don't have the words to describe what we're seeing. We're like scribes encountering a new civilization, trying to transcribe a language we've never heard before, making up new symbols for new sounds. This is the essence of scientific discovery. It's not just about finding new facts. It's about developing new frameworks to understand those facts. It's about realizing that the old map is wrong and having the courage to draw a new one, even if it means leaving parts of it blank for a while. Labeled with a humble "Here be dragons," 3 Atlas is one of those dragons. It's a creature that lives in the uncharted waters of our understanding, a reminder that for all our knowledge, for all our technology, we are still just beginners. We are still just children on the cosmic shore, picking up interesting shells and marveling at their strange shapes, without yet understanding the deep ocean they came from. And the most beautiful part of this is that the conversation is open to everyone. You don't need a PhD in astrophysics to listen. You don't need a $10 million telescope to participate. All you need is curiosity. All you need is a sense of wonder. All you need is the willingness to look up at the night sky and ask, what if? The citizen scientists who find the weird radio circles, the amateur astronomers who track comets from their backyards, the people who share these stories on social media and spark conversations and debates, they are all part of this dialogue. They are all contributing to our collective understanding. They are all scribes, helping to transcribe the universe's story. This conversation also forces us to confront our own place in the cosmos. For centuries, we saw ourselves as the center of creation, the purpose of the universe. Then science showed us that we live on a tiny planet, orbiting an average star in a typical galaxy among billions of others. It was a humbling realization, but in a way, the discovery of interstellar objects like 3 Atlas brings a new kind of significance. It shows us that the galaxy is interconnected, that what happens in one star system can, over billions of years, affect another. It suggests a kind of cosmic ecology, where materials, and maybe even the seeds of life, are constantly being exchanged, traded, and shared across vast distances. We are not isolated. We are part of a galactic community, a community of matter and energy that has been in motion for 13.8 billion years. The atoms in our bodies were forged in the hearts of stars that died billions of years ago, and now we are witnessing the arrival of new atoms, new molecules, new stories from other stars, other deaths, other births. We are, in a very real sense, participating in the life cycle of the galaxy itself. So, what is 3 Atlas telling us? It's telling us that the universe is more creative than we imagined. It's telling us that the rules we've derived from our one small solar system are not universal. It's telling us that there are processes at work in the galaxy that we have only just begun to glimpse. It's telling us to stay humble, to stay curious, and to keep listening. The conversation is ongoing. The universe is still speaking, and we, with our telescopes and our computers and our insatiable curiosity, are doing our best to listen, to learn, and to be worthy of the message. 3 Atlas is just one sentence in a story that will never end, and it's a privilege to be here to read it. Let's take a sharp turn away from the telescopes and the spectrographs for a moment, and look at the other side of this story, the human side, because the saga of 3 Atlas isn't just about data points and chemical anomalies. It's also about us. It's about how we process information, how we build narratives, and how we decide what to believe in a world that is increasingly complex and flooded with conflicting claims. We've already touched on the conspiracy theories that sprang up around the Blue Origin flight, and the pattern seeking that connects comets with planetary alignments. But this goes deeper. It's about the fundamental tension between skepticism and wonder, between the scientific method and the human desire for a good story. This tension is playing out in real time with 3 Atlas, and it's a fascinating case study in the psychology of belief in the 21st century. On one side, you have the scientific community, a group of people who are trained to be radically skeptical. Their entire worldview is built on a foundation of evidence, repeatability, and peer review. When they see the data from 3 Atlas, their first instinct isn't to shout "Eureka!" but to ask, how could we be wrong? They immediately start looking for errors. Is the spectrograph calibrated correctly? Could the nickel signal be a contamination from Earth's atmosphere? Is there a known physical process, however obscure, that could explain this? They build models, they run simulations, they propose hypotheses, and then they do everything they can to disprove their own hypotheses. It's a rigorous, often tedious, and self-correcting process designed to eliminate bias and get as close to the objective truth as possible. On the other side, you have a much broader, more diverse group of people. The public, the enthusiasts, the dreamers. Their approach is often driven by wonder, intuition, and a healthy distrust of authority. When they hear about a comet that's breathing water and glowing green with impossible metals, their first instinct isn't to look for an error, but to embrace the mystery. They see the possibility of something truly. They're more open to speculative ideas, to hypotheses that lie outside the mainstream. They're the ones asking, what if it's aliens? Not because they have evidence, but because it's a more exciting story. It's a more compelling narrative, and who can blame them? The scientific explanation, even when it's correct, can often sound dry and technical. Organometallic compounds sublimating at low temperatures doesn't have the same ring to it as a probe from an alien civilization. The narrative of a cover-up, of hidden knowledge, of a few brave souls speaking truth to a powerful establishment, is one of the oldest and most powerful stories we tell. It resonates on a deep, emotional level. This creates a chasm, a communication gap that is incredibly difficult to bridge. Scientists, trained in precision and caution, often use language that is filled with caveats and uncertainties. They say things like, the data suggests a high probability of ... double quotes, or one possible interpretation is ... They are trying to be accurate and honest about the limits of their knowledge. But to a public hungry for certainty, this can sound like waffling, like they don't really know what they're talking about. It creates an opening for others to step in with simple, confident, and often completely wrong explanations. This is where the machinery of modern information dissemination kicks in. And it's a machine that is not designed for nuance. Social media algorithms don't reward careful, measured analysis. They reward engagement. And nothing drives engagement like controversy, mystery, and conflict. A headline like "Scientists Baffled by Impossible Comet" will get 1,000 times more clicks and shares than one that says, "Comet exhibits unusual chemical properties requiring further study." The algorithm creates an echo chamber. If you engage with one conspiratorial video about 3E Atlas, the platform will show you 10 more. You'll be drawn into a self-reinforcing bubble where the speculative is presented as fact, and the scientific consensus is dismissed as a lie. In this world, the careful skepticism of a scientist isn't seen as a strength, but as a weakness or a sign that they're part of the cover-up. This isn't just happening with astronomy. It's happening with climate change, with medicine, with politics. It's a fundamental breakdown in our shared reality. But with something like 3E Atlas, the stakes feel different. It's not as immediately consequential as a pandemic or a war, but it touches on something profound: our relationship with the universe itself. Are we alone? Is the universe a place of wonder and intention, or a cold, random, and meaningless void? The answer you choose to believe says a lot about your worldview. And the data from 3E Atlas, in its ambiguity, provides a perfect canvas for people to project their own beliefs onto. If you believe the universe is full of life and intelligence, then the comet's weirdness is evidence of that. If you believe the universe is governed by predictable, natural laws, then the comet's weirdness is a puzzle to be solved. A challenge to our understanding. The tragedy is that these two positions don't have to be mutually exclusive. You can be a rigorous, evidence-based scientist and still be filled with a profound sense of wonder. You can believe that the universe is governed by natural laws and still be open to the possibility that those laws are far stranger and more creative than we currently understand. The best scientists are often the most awestruck people, because they are the ones who see, on a daily basis, just how much we don't know. The challenge for all of us, scientists and citizens alike, is to learn how to hold these two ideas in our heads at the same time, radical skepticism and radical wonder, to be able to look at the data from 3 Atlas and say, this is fascinating and mysterious, and we need to investigate every possible natural explanation before we even begin to consider anything more exotic, while also thinking, wow, isn't it incredible that we live in a universe where a thing like this can even exist? It's about finding the sweet spot between close-minded dogmatism and uncritical gullibility. It's about embracing the uncertainty, about being comfortable with the phrase, we don't know yet, because that phrase isn't an admission of failure. It's the starting line for every great discovery. It's the most honest and exciting thing a scientist or a curious person can ever say. 3 Atlas is forcing us to have this conversation, not just in academic journals, but in our group chats, on our social media feeds, and in our own minds. And that, in itself, might be its most important message to us. Every story has an ending, and the story of 3 Atlas, as seen from our little corner of the cosmos, is rapidly approaching its finale. It's on its final, fiery plunge toward the sun. Soon, it will reach perihelion, its closest approach, experiencing levels of heat and radiation it hasn't felt in billions of years, if ever. It will put on one last, spectacular show, a final burst of activity as it unleashes the last of its volatile reserves. And then, just as quickly as it arrived, it will be gone. It will swing around our star and begin its long journey back out into the interstellar void. Never to return, it will become fainter and fainter, a ghost receding into the darkness, carrying its secrets with it into the vast, empty spaces between the stars. We will watch it go, our telescopes straining to catch its last photons, until one day there's nothing left to see. The conversation will be over for now, but the legacy of 3 Atlas will remain. It will linger in the data, in the scientific papers, in the questions it forced us to ask, and in the new avenues of research it opened up. Its visit, however brief, will have a lasting impact on our understanding of the cosmos and our place within it. What will that legacy be? First and foremost, it will be a mountain of data. Every spectrum, every image, every measurement of its brightness and composition is a permanent record, a treasure trove for future scientists to analyze. Years from now, when we have better models, better computers, and new ideas, researchers will go back to the 3 Atlas data. They'll find things we missed. They'll see patterns we couldn't. They'll use it to test theories we haven't even conceived of yet. This data is a gift that will keep on giving, a scientific time capsule from a singular event. Second, its legacy will be a new set of questions. Before 3 Atlas, we had a neat, tidy model of how comets behave. That model is now, at best, incomplete. It's been shattered into a dozen pieces. Future research on comets, both in our solar system and beyond, will have to account for the impossible water production, the decoupled metals, the strange switch-on behavior. 3 Atlas has forced us to rewrite the textbooks, or at least to add a whole new, very strange chapter. It will inspire a new generation of cometary scientists, students who were captivated by this mystery and who will dedicate their careers to understanding it. Third, its legacy will be a profound shift in our perspective on interstellar objects. Before Oumuamua, they were a theoretical possibility. After Oumuamua and I Borisov, they were a confirmed reality. After 3 Atlas, they are a diverse, complex, and fundamentally important population of objects that we must study. It has cemented the idea that these aren't just rare oddities. They are a critical part of the galactic ecosystem. It has made the case for interceptor missions undeniable. The scientific payoff of getting a sample from an object like this is now so clear, so compelling that it's no longer a question of if we will try, but when and how. But perhaps the most important legacy of 3 Atlas is a more personal, more philosophical one. It's a legacy of wonder. In a world that can often feel cynical, divided, and focused on the mundane, this comet gave us something to look up to, literally. It reminded us that there are still things out there that can surprise us, that can make us feel like kids again, staring at the night sky in awe. It was a shared global experience, a mystery that belonged to everyone, from the professional astronomer at a major observatory to the amateur with a small telescope in their backyard to the person just scrolling through news on their phone. It reminded us that we are a species of explorers, that our curiosity is not a trivial trait, but a fundamental part of who we are. It's the same curiosity that drove our ancestors to migrate out of Africa, to cross oceans in small boats, and to set foot on the moon. That curiosity is now pointed at the stars, at objects like 3 Atlas, and it is that curiosity that will ultimately carry us forward as a civilization. The story of 3 Atlas is also a story about humility. It's a reminder that for all our knowledge, for all our technological prowess, we are still just scratching the surface of understanding the universe. The cosmos is not obligated to make sense to us. It is not required to follow the rules we've derived from our limited experience. It is wilder, stranger, and more creative than we can possibly imagine. And that's a beautiful thing. It means there will always be new mysteries to solve, new frontiers to explore, new wonders to discover. As 3 Atlas fades from view, it leaves us with a choice. We can go back to our daily lives, let the memory of this strange visitor fade, and move on to the next fleeting distraction. Or we can hold on to the feeling of wonder it inspired. We can use it as a catalyst to ask more questions, to support more science, to encourage more curiosity in ourselves and in others. We can see it not as an end, but as a beginning. The beginning of a new era in astronomy, where we actively hunt for and study these interstellar messengers. The beginning of a new understanding of our own solar system's place in the galaxy. The beginning of a new appreciation for the intricate, interconnected, and astonishingly creative processes that shape the cosmos. 3 Atlas came from the dark, and it will return to the dark. But for a brief, shining moment, it illuminated our world, our science, and our imaginations. It was a visitor, a messenger, a teacher, and its greatest lesson may be this, that the universe is full of stories, and we have only just begun to learn how to read them. The conversation isn't over. It's just getting started, and the next message from the void is already on its way. We'll be ready for it this time. We'll be listening. Long after 3 Atlas has faded into the blackness, becoming too faint for even our most powerful instruments to track, its true work will begin. The ghost of the comet will live on, not in the sky, but in servers, in hard drives, and in the minds of scientists around the world. The echo of its passage will resonate through the halls of academia for decades, a whisper of data that will shape the future of planetary science. This is the unseen life of a major astronomical discovery. The headlines fade, the public moves on, but for the researchers in the trenches, the real work is just beginning. The data from 3E Atlas is not a neat, tidy package. It's a chaotic, messy, and incomplete snapshot of a complex, dynamic object. It's a puzzle with most of the pieces missing, and the pieces we do have are from different boxes. The challenge is to assemble them into a coherent picture, and that challenge will fuel careers. Think of the spectroscopic data alone. It's a treasure trove, but it's also a nightmare of complexity. Every emission line, every dip and peak in the spectrum is a clue. But those clues are layered on top of each other. The bright green glow of nickel is mixed with the signature of cyanide, the faint whisper of water, and the overwhelming signal of carbon dioxide. Untangling this chemical knot will require sophisticated computer models, lab experiments that try to replicate exotic ices under alien conditions, and a level of ingenuity that we can't yet predict. A graduate student today, working on their PhD, might dedicate 5 years of their life to understanding just one aspect of this comet. Maybe they'll focus on the nickel anomaly. They'll spend their time in the lab trying to create organometallic compounds that could survive in deep space and then sublimate under sunlight. They'll run computer simulations of protoplanetary disks with different chemical recipes to see if any of them could produce a nickel-rich, iron-poor comet. Their dissertation, 100 pages of dense, technical writing, will add a small but crucial piece to the puzzle. And that piece might be the key that unlocks the whole mystery. Another team of researchers might focus on the comet's dynamics. They'll take the precise trajectory data, the measurements of its non-gravitational acceleration, the tiny push it gets from outgassing, and they'll run it backward in time. Not just a few thousand years, but billions. They'll model the gravitational influence of the entire galaxy, the spiral arms, the dark matter halo, trying to trace its path back to its birthplace. They'll never know for sure, but they might be able to say with high probability that it came from a specific region of the thick disk, a star-forming region that existed 7 billion years ago. They'll be telling the story of a long-lost home. Then there are the astrobiologists. They'll look at the organic molecules detected in the comet's coma. They won't find life, but they'll find the ingredients. They'll analyze the ratios of carbon, hydrogen, nitrogen, and oxygen. Comparing them to the ratios found in life on Earth, they'll look for specific molecules, like amino acids or nucleobases, that are known precursors to biology. Even if they don't find them, the absence of a signal is still data. It tells them something about the chemical pathways that are or are not common in other star systems. This is the slow, methodical, and unglamorous work of science. It's not a sudden eureka moment. It's a slow, grinding process of testing, failing, refining, and testing again. It's a global collaboration, with researchers from different countries, different institutions, and different disciplines, all working on different parts of the same problem, sharing their data, arguing over interpretations, and slowly collectively, building a better understanding. The legacy of 3E Atlas will also be written in the proposals for new telescopes and new space missions. The data from this comet will be used to justify the need for a dedicated interceptor mission. Scientists will write compelling proposals arguing that the scientific return from getting a physical sample from an object like this would be immense. They'll use the specific anomalies of 3 Atlas, the nickel, the carbon dioxide, the impossible water as the primary motivation. We need to go to one of these objects, they'll argue, because our ground-based and remote observations can only tell us so much. To truly understand these things, we need to touch them. These proposals will be debated, reviewed, and ranked. They'll compete for funding against other worthy scientific missions. It might take 10 years, 20 years, even longer, but eventually a mission like this will be approved. And when it is, when a spacecraft finally launches to chase down an interstellar visitor, the ghost of 3E Atlas will be there, a silent partner in the endeavor, the patient catalyst that made it all possible. The data will also change how we look at our own solar system. We'll go back and re-examine the data from our own comets, like Halley's Comet or Comet 67P Churyumov-Gerasimenko, which was visited by the Rosetta mission. We'll look for faint signals of nickel without iron that we might have missed before. We'll reanalyze the water production rates of comets at large distances, looking for subtle activity that we previously dismissed as noise. 3 Atlas would force us to look at our own backyard with new eyes, to question what we thought we knew, and to find that even the familiar is still full of surprises. In a way, the most profound impact of 3E Atlas will be on the next generation. The kids who were in elementary school today, who heard about this weird green comet on the news or saw a video about it on YouTube, will be the ones leading these future missions. They'll be the ones writing the computer code, designing the instruments, and interpreting the data from the next interstellar visitor. The sense of wonder that 3 Atlas sparked in them will be the fuel for their curiosity. It will be the reason they chose a career in science, technology, engineering, or math. This is how progress works. It's not a straight line. It's a winding path, marked by unexpected discoveries, strange anomalies, and the persistent, patient work of countless people over many years. 3E Atlas is not just a comet. It's a catalyst. It's a spark that has ignited a fire of inquiry that will burn for generations. The echo in the data will become a roar of discovery, and the story of this strange visitor will be told and retold, not as a closed chapter, but as an opening line in a much larger, more incredible story that we are only just beginning to write. And so we arrive at the end of this particular story, but not the end of the conversation. The tale of 3 Atlas, from its impossible signal to its final departure, is a microcosm of the entire human adventure in science. It's a story that begins with a strange light in the sky, moves through a period of intense curiosity, rigorous investigation, and wild speculation, and ends not with a final, neat answer, but with a deeper understanding and a whole new set of questions. It's a story that reminds us why we do this in the first place, why we point our telescopes at the heavens, why we spend billions of dollars on observatories and space probes, why we encourage our children to dream of the stars. It's not just for the data, not just for the technological spin-offs, not just for the knowledge. It's for the wonder. It's for the feeling of being part of something so much bigger than ourselves. Three-eyed Atlas is gone now, a ghost heading back to the dark. But it left something behind. It left a crack in the shell of our understanding, and through that crack we glimpsed a universe that is more diverse, more dynamic, and more mysterious than we ever imagined. It taught us that the rules we thought were universal are, in fact, local. It showed us that the chemistry of the cosmos is a rich and varied tapestry, and we've only seen a single thread. It also taught us about ourselves. It showed us the power of our pattern-seeking brains for better and for worse. It highlighted the tension between our desire for simple, exciting stories and the slow, messy, and often unsatisfying process of scientific discovery. It forced us to confront the challenges of communicating complex, uncertain ideas in a world that craves certainty and clicks. But most importantly, it reminded us to look up. In a world that constantly demands our attention be focused downward, on our screens, on our problems, on the endless churn of daily life. 3 Atlas was a call to lift our eyes. It was a reminder that there is a universe above our heads, a place of infinite beauty and profound mystery, and that we are, by some incredible stroke of luck, conscious beings who can appreciate it. The journey of 3 Atlas is a mirror for our own journey. It began in the dark, was ignited by a star, blazed with a unique and brilliant light, and then returned to the dark, leaving behind a legacy that would ripple outward for eons. We, too, have our brief moment in the light. We, too, have the chance to burn brightly, to ask questions, to learn, and to leave behind a legacy of knowledge and wonder for those who come after us. The next interstellar visitor is already on its way. It might be a decade away, or it might arrive next year. It might be even stranger than 3 Atlas, or it might be disappointingly normal. Whatever it is, we will be ready for it in a way we weren't before. Our telescopes will be more powerful, our detection algorithms will be smarter, our theories will be more flexible, and our sense of wonder, thanks to 3 Atlas, will be that much sharper. The conversation with the cosmos continues. It is the longest and most important conversation we will ever have. It is a dialogue that spans generations. A story that is written not in ink, but in light, in matter, and in the unquenchable curiosity of the human spirit. So, the next time you have a clear night, step outside, look up, find a planet or a constellation or just the vast, dark expanse between the stars, and think about 3 Atlas. Think about its impossible journey, its strange chemistry, and the profound questions it raised. And know that you are a part of that story. You are a participant in that great cosmic conversation. Because the final lesson of 3 Atlas is this: the universe is not something that happens to us. It is something we are a part of. We are made of star stuff, and we are the universe's way of knowing itself. Every question we ask, every mystery we solve, every piece of the puzzle we put into place is the universe becoming a little more self-aware. 3 Atlas spoke. We listened, and in the listening, we learned something not just about a comet from another star, but about ourselves. We learned that we are a species that looks at the impossible and says, "Let's figure it out." We are a species that looks at the darkness and says, "What's out there?" We are a species that, against all odds, looks up at the vast, silent cosmos and refuses to believe that we are alone, and that, in the end, is the most beautiful and important truth of all. The search continues, the wonder endures, and the story goes on.